Welcome in the first course of the series, in which we explore the atomic model. My name is Stéphane Pommet, and I'll guide you through the chart of nuclides and explain where nuclear energy comes from. First, we make a quick tour through tiny parts of matter called molecules, atoms, and nuclei. Molecules are the smallest units of a substance that exhibit its chemical properties. They consist of atoms of the same or different elements, joined together by electrostatic forces and by sharing electrons through covalent bonds. The atom resembles a solar system. In the middle, there's a heavy nucleus with a positive charge, and orbiting around it are small electrons with a negative charge. In a complete atom, the sum of the charges is zero. The electrons are arranged in orbitals defined by quantum mechanics. The size of the nucleus is in the femtometer range, which is 10,000 times smaller than the atom. The nucleus contains positively charged protons and uncharged neutrons, which both consist of quarks. The nucleons are held together at close range by the strong force. A nuclide is defined by two numbers: the proton number, which tells us to which element the atom belongs, and the mass number, which is the sum of protons and neutrons inside the nucleus. For example, carbon-12 is a light nuclide consisting of 6 protons and 6 neutrons. Uranium-235 is a heavy nuclide with 90 protons and 145 neutrons. For the same element, one can have atoms with a different number of neutrons. We call them isotopes. They have a different mass, but chemically behave the same. For example, the lightest element, hydrogen, has isotopes with 1 or 2 extra neutrons. They are called deuterium and tritium. Now that we know the structure of the atom, we can explore the chart of nuclides. In chemistry, we have the periodic table of elements, which is arranged according to nuclear charge number, and the groupings reflect the filling of electron shells around the nucleus. In a nuclide chart, all nuclides are plotted as a function of their number of protons and neutrons. There are roughly 3,000 nuclides, but most are unstable. Only the black dots in the chart represent stable nuclides. Stability is higher around magical numbers corresponding to full nuclear shells. Here we see a detail. The isotopes of one element are arranged in horizontal lines. The isotones are in one column and the isobars on a diagonal. The stable nuclides are indicated in black and the radioactive ones have a color code. Nuclear scientists often navigate through the nuclide chart to see how one nuclide transforms into another through radioactive decay. For example, beta-minus decay corresponds to a jump from the purple square to the orange. The same is done for nuclear reactions. This is handy for deciding how to produce a nuclide in the laboratory, but also to understand how nuclides are transformed in the reactors or stars. By the way, do you know where atoms come from? Well, only the lightest elements were produced after the Big Bang. The others have been synthesized by nuclear reactions in stars. And it takes really large stars and supernovae to produce the heaviest elements. Now you know, we are made of stardust. Last but not least, let's see where nuclear energy comes from. It has to do with Einstein's formula relating mass with energy. First, we define a unit of mass for the atom, which is 1/12 of the mass of a carbon-12 atom. This is roughly the mass of 1 neutron or 1 proton. A deuterium atom has a mass of about 2 atomic mass units because it has 1 neutron and 1 proton. The mass of an electron is 2,000 times smaller. However, the funny thing is that the sum of the individual masses of these 3 particles is higher than the mass of deuterium. So where is the missing mass? Well, here it is. The missing mass corresponds to the binding energy. The binding energy is the energy needed to pull each particle apart from the nucleus. Einstein's formula makes the link between the binding mass and the mass defect. The binding energy per nucleon is not the same in each nuclide. The most tightly bound nuclides have an intermediate size, like iron. The least tightly bound nuclides are light elements, like hydrogen, and the very heavy ones, like uranium. That means that binding energy can be gained through fusion of hydrogen or fission of uranium. This is fusion. By smashing deuterium and tritium atoms together, one makes a more stable helium atom and a neutron. The sum of their mass is lower because of the higher binding energy, and the mass defect is released as fusion energy. When a big uranium nucleus splits into two fragments and some neutrons, a lot of mass is converted into kinetic energy. This creates heat, which can be transformed into electricity. Thank you for watching this video. I'll let you reflect on it all with a picture of the remains of a supernova, the birthplace of our heavy elements. We are all stardust. Isn't it romantic? Hi, my name is Stéphane Pomé, and together with you, I want to explore radioactivity. Radioactive decay is a spontaneous stochastic process whereby an unstable nucleus transforms into another nucleus. Different types of ionizing radiation can be emitted, such as helium nuclei called alpha particles, high-energy photons called gamma rays, and electrons or positrons called beta particles. Radioactivity is omnipresent in nature. In soil, we find, for example, uranium-238, which decays to a series of other unstable nuclides. This decay chain stops when stable lead is reached. Each radionuclide has its own half-life, by which half of the atoms are expected to decay. Unlike with an hourglass, it is not so that all atoms are decayed after 2 half-lives. The number of surviving atoms follows an exponential curve. Radioactivity is used as a clock in geochronology. We know that Earth is 4.5 billion years old because all short-lived nuclides have decayed away, and only nuclides with long half-lives have survived with time. On the chart of nuclides, we can see the different types of radioactive decay. The black dots represent the valley of stability. In the purple region, nuclides are in excess of protons and decay by beta plus emission or electron capture to reduce the proton number. In orange are the nuclides with too many neutrons. They can convert a neutron into a proton by beta minus decay. The heavy nuclides in yellow and green can go on a nuclear diet by emitting a heavy alpha particle, or take a crash diet by splitting into 2 fragments. Beta minus decay is the only spontaneous process in which a nucleus can cure from neutron excess by transforming a neutron into a proton and emitting an electron and antineutrino from inside the nucleus. The mass number stays the same, so it is an isobaric process. The antineutrino cannot be detected, but we know that it takes away, on average, 2/3 of the released energy, leaving the beta particle with a remaining fraction, which can be any value between 0 and the Q value. In an energy diagram, we start from an unstable nucleus with a high energy, jump to a lower energy state in the daughter product, and possibly go further down by gamma transitions. Whereas the excitation energy is usually expelled through emission of gamma rays, sometimes the energy is converted to kick out an orbital electron, which is then called a conversion electron. Most excited levels in a nucleus are short-lived, but some live long enough to be called metastable states, and their decay is called isomeric transition. Beta plus decay is somewhat opposite to beta minus decay. It converts a proton into a neutron with emission of a positron and a neutrino. The positron is the antimatter counterpart of an electron and has a positive charge. There's also a difference with respect to the energy diagram. Beta plus decay requires 1 MeV for the creation of an electron-positron pair in the nucleus, so that less energy is available to the positron and neutrino. This is what happens with the emitted positron. It meets an electron, and together they annihilate, and matter is converted into pure energy in the shape of two 511 keV photons which fly away in opposite directions. Nuclear fireworks, which has a nice application in PET scanners for medical imaging. Beta plus decay has a competitor, namely electron capture decay. The nucleus steals away an electron from one of the inner atomic shells and then converts a proton into a neutron and emits a neutrino. After electron capture, the atom has some rearranging to do. If a K-shell electron has been captured, an electron of a higher shell will take its place, and an X-ray is emitted or an Auger electron. This results in 1 or 2 gaps in higher shells, which in turn have to be filled. Notice how atoms and nuclei de-excite in similar ways. When electrons rearrange in atoms, the keV excitation energy is taken away by X-rays or Auger electrons. When nucleons rearrange, gamma rays in the MeV range are emitted, or conversion electrons. Alpha decay is a sport played by the heavyweight class of nuclides. Excessive mass is lost by emission of a helium nucleus with a kinetic energy of 4 to 8 MeV. In classical physics, an alpha particle cannot escape from the nucleus because of the Coulomb barrier. In quantum mechanics, it is possible to tunnel through the barrier. Even heavier particle clusters can escape, but that happens very rarely. Then, what to think of spontaneous fission of a nucleus? This was believed energetically impossible at its discovery, but later it was realized that a potential barrier could be overcome if a big nucleus would stretch like a water drop into a dumbbell shape and then break apart. In reactors, fission is induced by neutrons, which give the nucleus that extra binding energy it needs to pass the barrier. And with this bombshell, we have reached the end of this decadent course. Thank you for your attention, and don't lose your excitement.
A radioactive source can emit different types of radiation, such as alpha particles, gammas, or beta particles. The question now is, what will happen when these particles pass through matter? My name is Jan Heijsen, and in this video we will discuss the interaction of radiation with matter. When radiation passes through matter, it will interact with the atoms of the material it passes through. How will it interact, and how probable is the interaction? This will depend on the type of energy of radiation and the type of matter it is passing through. Charged particles and photons will mainly lose energy or be scattered by interactions with the electrons circling the atoms of the material they pass through. We can state that their interaction is mainly determined by atomic physics. The ways of interaction can be subdivided in 2 large groups, depending on the type of particle. When a particle passes through a slab of matter, it can either undergo a large number of small interactions in which it is scattered slightly and loses a small part of its energy during each interaction, or it can be eliminated in a single all or nothing interaction. Let us consider now a parallel beam of monoenergetic particles. In the case of particles undergoing multiple small interactions, the energy of the particles will be degraded. There will be a spread on the energy of the particles in the beam after passing through the slab of material. By increasing the slab thickness, particles will lose more and more energy. As long as the particles do not lose all of their energy, all particles will pass through the slab of material. Starting at a certain slab thickness, some of the particles will have lost all of their energy. They will be fully stopped in the material. If we keep increasing the thickness of the slab, more and more particles will be stopped until eventually no more particles are passing through. The average thickness at which the particles in the beam are stopped is called the range. This range is typical for this particular type of radiation with this specific energy in this specific material. In the case of particles undergoing all or nothing interactions, the characteristics of the beam passing through the slab will be different from the previous case. Since in this case particles can pass through the slab of material without undergoing any interaction, the transmitted beam will have the same average energy as the original beam. However, some of the particles are eliminated in all or nothing interactions, so the number of particles passing through will decrease when the thickness of the slab increases. The number of particles that interact in a slice of material is proportional to the number of incident particles and to the thickness of the slice. Therefore, the number of transmitted particles will decrease exponentially with the thickness of the material. In this case, no range can be defined, but rather an attenuation coefficient mu and a mean free path, which is the average distance traveled by a particle before it interacts. The value of this mean free path is given by 1 divided by mu. Let us now discuss some radiation types in more detail. We will focus on the interaction of the 3 specific types of radiation we mentioned earlier. Heavy charged particles, such as alpha particles, high energy photons, called gamma rays, and electrons or positrons, called beta particles. Heavy charged particles lose their energy mostly through many small collisions with bound electrons in the material via Coulomb or electromagnetic interaction. The charged particle can lift a bound electron to a higher energy state and leave an atom of the material in an excited state. It can also strip an electron from the atom, in which case we talk about ionization. Photons interact with matter through 3 main processes: the photoelectric effect, the Compton effect, and pair production. In the photoelectric effect, a photon is absorbed by an atom, which in turn emits a bound electron. In the Compton effect, the photon bounces off a free electron. In matter, electrons are not really free but bound to atoms. However, if the photon energy is high enough, the binding with the atom can be neglected. The photon is scattered and will transfer a part of its energy to the electron. During pair production, a photon with sufficient energy will produce an electron-positron pair according to Einstein's well-known equation E equals mc squared. In order to conserve energy and momentum, this can only occur in the electromagnetic field of an atomic nucleus. In 2 of the 3 cases discussed above, the photon is eliminated during the interaction process. Also in the case of Compton scattering, the scattered photon can be eliminated in a subsequent photoelectric effect or pair production event. Therefore, the all or nothing type of interaction is a good approximation for the interaction of photons with matter. The 3 processes have very different energy dependencies. The photoelectric effect will dominate at lower energies. At these energies, the Compton effect is rather small in comparison, but it becomes more important at intermediate energies. For sufficiently high energies, pair production becomes the dominant process. The attenuation coefficient μ for photons can thus be written as a sum of 3 terms. To conclude, let's have a look at electrons and positrons. At lower energies, they lose their energy through collisions when passing through matter, just like heavy charged particles do. During these collisions, they can excite or ionize the atoms in the matter they've passed through. Above a certain critical energy, an additional energy loss mechanism becomes important: Bremsstrahlung. In this process, electromagnetic radiation is emitted due to the acceleration or deceleration of the electron or positron in the electromagnetic field of a nucleus. The total energy loss of electrons and positrons is therefore the sum of 2 parts: a collision term and a radiation term. And with these particles, we have reached the end of our overview of how radiation interacts with matter. Thank you for your attention.
This video will give you an introduction on radiation protection dosimetry. Basically, it deals with quantifying the health effects induced by the radiation to which radiation workers, for instance in the nuclear or medical field, are being exposed. Why do we actually need radiation protection dosimetry? Well, ionizing radiation can induce a variety of detrimental health effects such as skin burns, cataract, or cancer. These effects fall in 2 categories. Firstly, we have the deterministic effects, such as burns, cataract, and in very severe cases also hair loss and organ failure. These effects all have a certain threshold dose. Below the threshold dose, these effects do not occur at all, while above the threshold, they occur with certainty, and the severity increases with the dose. Deterministic effects typically appear immediately. Only cataract needs some decades to develop. Besides the deterministic effects, we also have the stochastic effects, such as cancer and inheritable effects. These have no threshold dose and can occur even at very low doses. On the basis of epidemiological studies, it is usually assumed that the chance for stochastic effects increases linearly with the dose. So in contrast to the deterministic effects, it is now the probability and not the severity of the effects that increases with the dose. Stochastic effects typically also need several decades to develop. It is thus clear that we have to protect radiation workers against these health effects. Radiation protection is based on 3 pillars. Firstly, one should always justify the use of radiation. Secondly, one should always keep radiation dose as low as reasonably achievable. This is known as the LWR principle. And thirdly, legal dose limits are imposed, such that deterministic effects cannot occur and the chance for stochastic effects remains at a tolerable level. Both the LWR principle and the dose limits require, of course, that we have measurable quantities quantifying the radiation-induced health effects. This is where radiation protection dosimetry comes into play. How can we express and measure the radiation doses to which workers are being exposed? In order to properly quantify radiation-induced health effects, 3 aspects have to be taken into account. Firstly, the amount of radiation energy deposited in each of the tissues of the exposed body has to be assessed. This is characterized for each tissue by the organ absorbed dose. This quantity gives you the amount of radiation energy deposited in the tissue T per unit of mass. It is expressed in joule per kilogram, which has been given a special name, Gray. Secondly, one has to take into account the harmfulness of radiation. Some radiation types, such as photons and electrons, have a low ionization density on the scale of a DNA molecule. This gives rise to simple DNA damage that can usually be repaired by the body. On the other hand, radiation types, such as alphas and heavier nuclei, have a much larger ionization density. This gives rise to very complex DNA damage that is much more difficult for the body to repair and thus more harmful. The harmfulness of each radiation type R is taken into account by the radiation weighing factor. This quantity expresses how much more damaging a radiation type is in comparison for photons for the same organ absorbed doses. It is a dimensionless number. As you can see in the table on the left, electrons and muons have the same weighing factor as photons. Protons and charged pions are 2 times more harmful. Alphas and heavier nuclei even are 20 times more harmful. For neutrons, the weighing factor depends on the energy, as shown in the plot on the right, and ranges about 2.5 up to slightly above 20. Thirdly, for stochastic effects, one has to take into account the radiosensitivity of the affected tissues. The radiosensitivity of each tissue is expressed by the tissue weighing factor. This quantity expresses which fraction of the stochastic effects occurs in tissue T for a uniform whole-body radiation exposure, and is again a dimensionless number. In the table on the left, you can see, for instance, that there is 12 times more chance for stochastic effects in the red bone marrow or in the stomach than in the brain or the skin. Now, with the organ-absorbed dose, the radiation and tissue weighing factors, we can construct the two main quantities of radiation protection dosimetry. The deterministic effects in a tissue T are quantified by the organ equivalent dose. This first quantity is calculated by multiplying the organ absorbed dose for a tissue T with the radiation weighing factor, and sum the contributions for the different radiation types. It is expressed in joule per kilogram, and it has been given the special name sievert. In some specific workplaces, such as nuclear medicine and interventional radiology, the hands and the islands are the most exposed tissues of the worker's body. As these tissues are more sensitive for deterministic effects than for stochastic effects, one monitors the organ equivalent dose. This is done with small luminescent radiation detectors worn in a ring holder at the base of the index or on a band around the head, as close to the eye as possible. The stochastic effects for the whole body combined are quantified by the total effective dose. This second quantity is calculated by multiplying the organ equivalent doses for all tissues with the tissue weighing factor, and then sum all the contributions for all tissues. The effective dose is also expressed in sievert. Epidemiological studies have shown that there is about 5% additional cancer risk per sievert of effective dose. So multiplying the effective dose with 5% gives you an indication of the additional cancer risk induced by the radiation exposure. The effective dose is monitored for all radiation workers. This is done with a compact passive whole-body dosimeter, worn at chest level. Most whole-body dosimeters are also based on luminescent detectors. It is also possible to place environmental dosimeters at a certain location to estimate the effective dose to which people there will be exposed. Workers at risk of internal contamination with radionuclides also have to be monitored for internal radiation exposure. For gamma emitters, this is done by measurement of the worker with an external detector close to the body. For pure alpha and beta emitters, this is done by dissolving urine samples in scintillation liquid. Such measurements allow calculating the committed effective dose to which the worker will be exposed over the course of his life due to incorporation of radionuclides in his body. So now you've had a first glimpse on the complexity and importance of radiation protection dosimetry.
When charged particles or photons pass through material, they mostly interact with the electrons of the atoms in the material. But what will happen when particles manage to pass through the electron cloud and reach the heart of the atom, its nucleus? My name is Jan Heijsen, and in this video we will discuss nuclear reactions and the fission process. When a particle and a nucleus get sufficiently close, a nuclear reaction might occur. Charged particles need to overcome the electromagnetic interaction with the atomic electrons and the nucleus to get close enough. Uncharged particles, like neutrons, do not have this problem and will reach the nucleus more easily. In a nuclear reaction, a projectile A hits a nucleus X, resulting in a nucleus Y and one or more ejectiles. The general notation for such a reaction is X, AB, Y, or A plus X leading to Y plus B. A and B can be a neutron, a proton, beta particle, a gamma, but also a heavier particle or nucleus. For a nucleus X, we usually call Z the number of protons, N the number of neutrons, and A the total number of nucleons or the atomic mass. For nuclear reactions, a number of conservation laws apply. The conservation of charge states that the total charge before and after the reaction should be equal. Also, the total number of nucleons before and after the reaction should be the same. During a nuclear reaction, mass can be converted into energy, or vice versa, according to Einstein's famous formula E equals mc squared. We define the Q value of a reaction as the difference between the mass after and before the reaction, multiplied by c squared. As such, it corresponds to the amount of mass that was converted into energy during the reaction, or vice versa. If Q is positive, the reaction is called exothermic, which means energy is produced during the reaction. If Q is negative, the reaction is called endothermic and energy is consumed. The law of conservation of energy states that the total amount of energy before and after the reaction should be equal. As a consequence, any energy produced or consumed has to come from the kinetic energy of the particles involved. Now, what is the probability that a nuclear reaction will take place? Let's start from a classical equivalent. Consider a very thin slab of material with an area given by A and a thickness given by dx. Particles are distributed across the slab with a particle density n, which is the number of particles per unit of volume. We define the cross-section sigma of a particle as the area covered by one particle in the plane of the thin slab. The total area covered by the particles is given by the number of particles multiplied by the cross-section of one particle. The fraction of the slab covered by particles is now given by the ratio between the area covered with particles and the total area of the slab. When a point-like projectile is passing through the thin slab of material, the probability that it encounters one of the particles in the slab is exactly given by this particle fraction. When n particles pass through the slab, a good approximation for the number of projectiles that will hit a particle in the slab is given by n times this particle fraction. In analogy with this classical case, for a nuclear reaction, we define the microscopic cross-section sigma as an effective area, which gives a measure for the likelihood that the projectile will react with the nucleus. The macroscopic cross-section is defined as sigma times the particle density n. All particles involved are tiny. Therefore, a new unit for nuclear cross-sections is defined, a barn, which is equal to 10 to the minus 28 squared meters. A projectile can react with the nucleus in different ways, called reaction channels, each leading to different ejectiles or different reaction products. For every channel, a partial cross-section is defined. The total cross-section is the sum of all partial cross-sections. Let's now have a closer look at nuclear reactions for which the projectile is a neutron. When a neutron interacts with the nucleus, an intermediate or so-called compound nucleus is formed. This compound nucleus might decay through a number of channels. Elastic scattering by emission of a neutron, capture by emission of a photon, fission by splitting in two, inelastic scattering by emission of a neutron and a photon, and charged particle reactions in which a proton, a deuteron, an alpha particle, or another particle is emitted. If we look at an example of a neutron-induced reaction cross-section, we see that the cross-section varies strongly with incident neutron energy. We notice a thermal region with a rather smooth variation at low energy, a resonance region in which the cross-section peaks at specific resonance energies, and an average region at higher energies where the cross-section is smooth again. We also notice that the value of the cross-section is different for different reaction channels. Let us now focus on the neutron-induced fission process. In this process, the compound nucleus splits into two fission fragments and a number of neutrons given by nu. The mass of the two fission fragments varies from fission event to fission event. If we plot their mass distribution, we notice two peaks, one for light fragments and one for heavy fragments. For each fission event, however, the total number of protons and the total number of neutrons before and after fission has to be conserved. The number of neutrons produced during fission also varies for each fission event. If we take the average, we typically obtain a value between 2 and 4, depending on the fissioning nucleus. Neutrons produced immediately during fission are called prompt neutrons. Apart from that, most fission fragments will be radioactive and will decay after the fission event. During some of these decay events, additional neutrons are emitted. These are called delayed neutrons. To conclude this video, let's have a look at how nuclear fission is used to produce energy on a large scale. A fission reaction is an exothermic reaction with a Q value of about 200 MeV. This energy is released as kinetic energies of the fission fragments and the neutrons, by emission of gamma rays, and by the decay of the fission fragments. To produce a significant amount of energy, a chain reaction is needed, in which neutrons from one fission event trigger the next fission event. In a nuclear reactor, a chain reaction is maintained with a huge number of neutrons and nuclei, leading to the production of energy on an industrial scale. The details of nuclear energy production will be discussed in further videos. For now, we have come to the end of our overview of nuclear reactions.
Hello, my name is Jan Kloosterman, and in this video I will explain you the life cycle of a neutron in a nuclear reactor core. This picture explains the nuclear fission event in a nuclear reactor. When a slow neutron is absorbed by a uranium-235 atom, it adds so much binding energy to the nucleus that the uranium atom can fission in two parts, the so-called fission products. In this process, on average, 2.5 neutrons are released. In the picture I've shown 3 new neutrons. Obviously, we need only 1 neutron to sustain the fission chain reaction. So what happens to the rest? This I will show you later on. But first we have to explain the characteristics of fission neutrons. This plot shows the energy distribution of the free neutrons when they are released in a fission event. The most probable energy is the value at a peak energy at around 700 kV, while the average energy reaches a value of about 2 MeV. Previously, you've heard about fissile nuclides, like uranium-235, which have a very high probability to fission when they absorb a thermal neutron. To enhance fission, we have to slow down the fission neutrons to energies below 1 eV. Because neutrons lose a lot of energy when they collide with hydrogen atoms, water is a very good moderator. And in many reactors, the coolant acts as a neutron moderator as well. When we moderate a neutron, this means we let it collide with nuclides like hydrogen to reduce its energy. They have to travel through the energy range in which the uranium-238 has many resonances. And when a neutron has an energy in the peak of one of these resonances, the probability it will be absorbed is very high. While for other values this probability is very low. This plot shows the processes of a neutron between its release as a free neutron and the moment it is absorbed in the reactor core or leaks away out of the reactor core. A fission neutron is released at very high energy of about 2 MeV, and by elastic and inelastic collisions it will lose energy and reach the resonance range of the uranium-238. Here, the neutron can lose energy via elastic collisions with the moderator, or it can be absorbed in the uranium-238 resonances. In the latter case, the neutron is lost for the chain reaction. Of course, this is also the case when a neutron leaks away from the reactor core. When the neutron survives the resonance range, it will reach the thermal energy range, and this range is very special, because the moderator atoms have an energy comparable to that of the neutrons, which means a neutron can also gain energy in a collision. But eventually, all thermal neutrons will be lost via absorption in the reactor core or via leakage out of the core. We will now follow the fission neutrons in more detail between birth and death. When the neutrons are released at high energy, some of them will be absorbed by uranium-235 or by the uranium-238. And although the chance is not very high, some of these absorption processes can lead to fission of uranium. In this case, we will gain some neutrons. And if we start with n neutrons, this number will be multiplied by the fast fission factor epsilon, which has a typical value of around 1.1. When the neutrons still have a high energy, they can escape from the reactor core. The fraction of neutrons that survives leakage is called the non-leakage probability. And because we speak here about fast neutrons, this fraction is called the fast non-leakage probability. As mentioned before, the neutrons that slow down have to cross the resonance region of the uranium-238 in the fuel. A certain fraction of the neutrons will be captured, while a fraction p, called the resonance escape probability, will survive the resonance range. The number of neutrons indicated on the right-hand side of the square have survived the resonances and will reach the thermal energy range. The thermal neutrons can disappear from the reactor core either by leakage or by absorption. The fraction that survives leakage is called the thermal non-leakage probability, indicated with the red capital P in the formula. And the remainder of the neutrons will be absorbed. However, we can distinguish between absorption by the structural materials at one side and by the fuel nuclides at the other. The fraction of the neutrons absorbed by the fuel nuclides, this is the uranium-235 and the uranium-238, is called the thermal utilization factor. And finally, we can calculate the number of fission neutrons released when one neutron is absorbed in a fuel. And this factor is called the neutron reproduction factor. Note that this is less than the neutrons released in a fission event, because part of the neutrons absorbed in the fuel will not lead to a fission event. The neutrons absorbed by the uranium-238 will disappear without fission. We can now wrap up by calculating the ratio of the number of neutrons at the end of the neutron lifetime and the number of neutrons we started with. And this ratio is defined as the effective multiplication factor, K effective, and is given by the 6-factor formula on this slide. If you would have an infinitely large reactor with no spatial leakage, the fast and thermal non-leakage probabilities would both be unity, and we would get the so-called 4-factor formula, which gives an expression for the infinite multiplication factor. From the multiplication factor we can derive another parameter that is closely related, namely reactivity. The reactivity of a nuclear reactor core is defined as a ratio of K effective minus 1 and K effective, as shown in the formula on the slide. If reactivity is larger than 0, the neutron flux increases with time. If it's less than 0, it decreases in time. Only if the reactivity is exactly equal to 0, the flux remains stationary. I want to end this video with a question for you to think over. What is the maximum theoretical value of the reactivity? In this movie, I will explain the neutron diffusion equation that can be used to calculate the power distribution in a nuclear reactor core. First, we define the neutron flux density, sometimes briefly called the neutron flux. In contrast to other fields in physics, the neutron flux density is not a vector, but a scalar. It's equal to the product of the neutron density and the velocity of the neutrons. Therefore, it can be viewed of as the total distance traveled by all neutrons in a unit volume per unit time. Typically, the neutron flux density is depending on space, energy and time. For simple applications with no energy dependence, the one-group approximation can be used, in which it is assumed that all neutrons have the same energy. In the remainder of this video, we will adopt this one-group approximation. The definition of the neutron flux density is illustrated in this figure. Suppose we have an arbitrary volume traversed by neutrons. If we sum the segments of all neutrons through the volume per second and divide by the size of the volume, we get the neutron flux density. It's the total distance traveled by all neutrons per unit volume and per unit time. Previously, we have seen that a microscopic cross-section of a nuclide is the effective area of the nuclide for interaction with neutrons. You can easily imagine that the number of reactions of a neutron beam with the atoms in a material will be proportional to this microscopic cross-section, but also to the atomic density of the material. The product of these two factors is called the macroscopic cross-section of the material. And we will use this macroscopic cross-section on the next slide to calculate the reaction rate density in the material. On the previous slides, we've seen that the neutron flux density is the total distance traveled by all neutrons per unit volume and per unit time, and that the macroscopic cross-section is the interaction rate per unit distance traveled by the neutrons. This means that the product of these two factors gives the total number of reactions per unit volume per second, and this parameter is called the reaction rate density of the neutrons. Because the neutron flux depends on space, energy and time, and because the macroscopic cross-section typically also depends on space and energy, the reaction rate density is also depending on these parameters. Because the macroscopic cross-section can be split into the individual contributions due to neutron capture, fission and scattering, also the reaction rate can be subdivided in these two separate contributions. And the units of these partial contributions are the same as for the total reaction rate. And the sum of all partial reaction rates is equal to the total reaction rate. Now we will derive an expression for the leakage of neutrons from a volume element. For simplicity, we will derive this expression in one dimension first. Imagine neutrons streaming from left to right. If the neutrons streaming out of an element delta X is larger at the right boundary than it is at the left boundary, there is a net positive outflow of neutrons. The leakage per unit size of the element, delta X, is equal to the derivative of the neutron current, called J. On the next slide, we will derive a simple expression for the neutron current based on Fick's law. Now we will derive an expression for the flow of neutrons from one region to the other. In the fusion theory, the transport of particles is described as being proportional to the gradient of the particle number density. In reactor physics, this would translate into a neutron current density that is proportional to the gradient of the neutron flux density. The formula for J gives the expression in one dimension, namely in the x direction. We will now derive a neutron balance equation in the fusion theory by looking at each loss and gain term in a unit volume. Left of the balance is a time derivative of the neutron number density. If this time derivative is 0, we have a stationary neutron flux, otherwise it is increasing or decreasing in time. The first term on the right-hand side describes the flow of neutron in the x direction. We would have similar terms with y and z in a three-dimensional problem. The term in blue between brackets is a neutron current density in the fusion theory using Fick's law. Note that we have two minus signs here because the leakage is counted as a loss term in the balance equation, which adds another minus sign in front of it. The second term on the right-hand side is the absorption rate of neutrons, which is also a loss term, and which has therefore also a minus sign in front of it. And the third term on the right-hand side is the fission neutron source term. This is equal to the fission rate density multiplied by the average number of neutrons released in a fission event, indicated by nu. For most reactors using uranium as a fuel, nu has a value of about 2.5. This equation shows the same expression for the three-dimensional case, where d phi dx is now replaced by the nabla operator. Nabla stands for the three-dimensional derivative in all three directions, X, Y and Z. If we would have a homogeneous reactor core, the diffusion coefficient would not be spatially dependent anymore, and the equation would become as in the bottom line. There is one important step to make. In the design process of a nuclear reactor core, it would be very difficult to find a fuel composition that would make the reactor core exactly critical, and the neutron flux density independent of time. Therefore, we apply a kind of trick. We adapt the production of the fission neutrons a bit, such that the production rate of fission neutrons at one hand balances the leakage and absorption rates of the neutrons at the other. For this purpose, we add the factor in red, 1 divided by k, in front of the fission neutron production term. K is equal to the production of neutrons in fission events divided by the loss of neutrons due to leakage and absorption. Is therefore equal to the effective multiplication factor that we've seen before in the video on the neutron life cycle. From the neutron flux density, we can calculate the power density in a reactor core. There is a simple relationship between the neutron flux density and the power density by first calculating the fission reaction rate and multiplying this with the energy release per fission. I want to end this video with a question to think over. Our research reactor at TU Delft has a power of 2 MW. How many grams of uranium do we fission per day? In this video, I will explain the operating principle of a nuclear reactor. Let's first recap a bit the fission chain process in a nuclear reactor core. If a slow neutron hits a uranium-235 nucleus, it will lead in 9 out of 10 cases to nuclear fission. In this process, 2 fission fragments are produced, the brown bullets, and on average 2.5 fission neutrons. The probability for a fast neutron to be absorbed by another uranium atom is very small, and therefore we have to try to slow down the neutrons by letting them collide with light nuclei, like hydrogen or carbon, a process which is called moderation. The slow neutrons, after moderation, can easily be absorbed by uranium-235. Of course, in each generation, we need an equal amount of fission reactions for a constant power production. So the other neutrons will have to leak away or need to be absorbed, for example, by the control rods or by the uranium-238 in the fuel. In the latter case, uranium-239 is produced, which decays after 2 steps into plutonium-239, which is also fissile and which can be fissioned in the next generation of fission processes. The fission process takes place in a nuclear reactor core, which is positioned in a reactor vessel on this figure. The red-yellow circuit is called the primary loop and contains water with a pressure of 150 bar and temperature of about 300 degrees Celsius at the core inlet and 330 degrees Celsius at the core outlet. The heat is transferred to a secondary loop with lower pressure, leading to the formation of steam that drives the turbine. A generator connected to the shaft of the turbine produces electricity. After expansion, the steam is condensed to water and pumped back to the steam generator. On top of the reactor vessel, you see the control rods, which contain neutron-absorbing materials and which can be inserted in the reactor core to control the reactor power. In addition, there is boric acid dissolved in the primary water, acting as a neutron absorber. The concentration of it can be reduced slowly during operation to compensate for the buildup of the fission products in the fuel and for the reduction of the fissile isotopes during burnup. Here you see how the fuel looks like. Small fuel pellets with a height of about 10 mm and diameter of 8 mm are stacked upon each other in a gas-tight fuel cladding. See the middle figure. The fuel rods are assembled together into fuel elements, and water flows through the space between the fuel rods to moderate the neutrons and to take away the heat. Another type of reactor also works with water as a coolant, but at a lower pressure of around 70 bar and a temperature of about 285 degrees Celsius. As a result, the water starts to boiling in the reactor vessel, and the steam produced drives the turbines directly. Because both the pressurized water reactor and the boiling water reactor use ordinary water, also called light water, as a coolant and moderator, they both belong to the class of light water reactors. This figure gives the number of neutrons per absorption in a fuel nuclide. It includes the effect that some neutron absorptions do not lead to fission, but to neutron capture. For a stationary fission chain reaction, the value of the number of neutrons per absorption should be larger than unity, because at least one new neutron is needed for a fission event in the next generation. If the line is above 2, there is one neutron left to convert uranium-238 into the fissile plutonium, or to convert thorium-232 into fissile uranium-233. In principle, breeding is possible then, meaning that the number of fissile isotopes in the fuel increases. As you can see, this parameter is strongly dependent on energy. If the neutron initiating a new fission is thermal, the thorium fuel cycle is most beneficial, while in the fast energy range, the uranium-plutonium fuel cycle has preference. In that range, the plutonium isotopes give considerably more neutrons per fission than the uranium isotopes. Here we show the principle of the fission chain reaction again. Let's first simplify the scheme a bit by omitting in the plot the two intermediate decay steps from uranium-238 to plutonium-239. In a fast reactor, we use no moderator to slow down the neutrons. Of course, the probability to fission uranium-235 becomes much smaller in this case, and we compensate this by increasing the fuel enrichment from 5 to about 15 to 20% in a fast reactor. In this way, we can compensate for the lack of moderation, and a fission chain reaction is still possible. Here we see the scheme for a fission chain reaction for a reactor fueled with uranium-235 and own-bred plutonium-239. I want to emphasize one important thing. We have seen that the plutonium isotopes produce more neutrons in a fission event if the neutron that causes the fission has a higher energy. And this is highlighted at the right bottom part of the plot. Now imagine we would use plutonium-239 right from the beginning of reactor operation. In that case, we have many more fission neutrons in each generation, and the possibility to breed more plutonium than we consume. We have then made a fast breeder reactor that produces more plutonium than it consumes. The concept of a fast breeder reactor is illustrated in this figure. In each fission event, we produce so many neutrons that we convert more uranium-238 into plutonium than we consume. So this video I want to end with a question. What is the maximum number of uranium atoms we can convert to plutonium per fission event?
What is a nuclear reactor made of? In this lecture, you will learn about the main types of nuclear reactor materials and their specific characteristics. The safety and economics of light water reactors rely on the performance of the materials used in the reactor. These materials must resist extreme conditions such as high temperatures and gradients, a corrosive environment, and intense radiation fluxes. The degradation of materials can lead to reduced performance and, in some cases, failure. We will discuss the materials used for the nuclear fuel, the cladding, the moderator, the coolant, the control systems, and the out-of-core structural materials. In this lecture, we will look at the nuclear fuel and the cladding. Nuclear fuel requires a fissile isotope to sustain the fission chain reaction. Uranium-235 is the most widely used fissile isotope. Natural uranium contains about 0.7% uranium-235 and 99.3% uranium-238. Alternative fuels can use the isotopes 239 of plutonium or 233 of uranium, but these do not occur in nature. Metallic uranium was used in the early reactors as nuclear fuel. However, metallic uranium is particularly sensitive to irradiation effects, and nowadays ceramic uranium dioxide is used instead. To sustain the fission chain reaction, the natural uranium is enriched during the fabrication process to a concentration of about 3 to 4% uranium-235. The fuel is in the form of pellets with dished faces to accommodate the radial anisotropic expansion during irradiation. The density of the pellet is around 95% of the theoretical density. The remaining 5% porosity serves as a sink for the fission gases produced during irradiation. As for the microstructure, the fuel is made of grains with a size of 8 to 10 micrometers. In the fuel rod, the uranium dioxide pellets are stacked on top of each other and are enclosed in a metallic structure called the cladding. The cladding isolates the fuel from the coolant. A small gap of about 80 to 100 micrometers is left between the pellet and the cladding. This gap is needed to facilitate the loading of the pellets and to anticipate the swelling of the pellets during irradiation. The pellets are kept in place in the rod by a metallic spring that is mounted on top of a pellet stack. The free volume around the spring, called the plenum, is used as buffer volume for the fission gases that are released during the irradiation. This avoids that the pressure inside the rod rises to unacceptable levels. Before closing, by welding the end plug on the top, the rod is pressurized with helium gas at 20 to 25 bars to ensure that the fuel cladding gap and the plenum are filled with gas. Helium is chosen as it is inert and has the best thermal conductivity among the inert gases. The dimensions of the fuel rod depend on the reactor designs. In pressurized water reactors, the fuel rods are about 4 to 5 meters long and have a diameter of 9 to 11 millimeters. In the fuel assembly of a pressurized water reactor, 179 to 264 fuel rods are arranged in a 17 by 17 square geometry and are held together by several spacer grids. The assembly also contains several control rods and a top and bottom nozzle for the coolant. In total, there are 150 to 250 of these fuel assemblies in the reactor core. The cladding material must meet several criteria with respect to its nuclear and material properties. Its constituting elements must have low neutron capture cross-sections, it must be compatible with the coolant, have favorable physical properties, especially high thermal conductivity and high melting point, a good mechanical stability, a good radiation stability, and a low permeability for fission gases and helium. In practice, only a limited number of elements fulfill these criteria. Zirconium was historically chosen as an advantageous material. However, this needs to be a special grade of zirconium with a very low content of hafnium. Hafnium is an element with very similar chemical properties, but with very different nuclear properties. It is a strong neutron capturing material. Pure zirconium metal is too brittle for practical use, however. Zircalloy, an alloy of zirconium and tin, has been developed to overcome this shortcoming. But this alloy did not have a high corrosion resistance towards the cooling water. Other forms of zircalloy have therefore been introduced in which small additions of iron, chromium and nickel significantly improve the properties. Zircalloy 2 is used in boiling water reactors, while zircalloy 4 is used in pressurized water reactors. With the increasing target burn-up of the fuel, the demands on the corrosion resistance have increased further, and nowadays alloys of zirconium with niobium have been introduced under the commercial names Stirlo, M5 or E110. Choosing the appropriate cladding material is crucial for the safety of a reactor. After our first lecture on nuclear fuel and cladding, we will now discuss the remaining types of in-core and out-of-core materials. We will discuss successively the materials used for the moderator, the coolant, the control systems, and the out-of-core components. The moderator is used to slow down the fast fission neutrons from their high kinetic energies of about 2 MeV to thermal energy ranges around 25 MeV. This process is called neutron moderation and is realized by the elastic collisions of the neutrons with the nuclei of a moderator. At each collision, a neutron transfers part of its energy to the moderator. Good moderators have a high scattering cross-section, but a low absorption cross-section, since absorption leads to transmutation and unwanted fission products. They are found on the upper left corner of the figure. In addition, the effectiveness of the moderation depends on the mass of the nucleus. Good moderators have a low mass because in that case, less collisions are required for moderation. The most used moderator is water, which also acts as a coolant. The coolant allows the extraction of the thermal energy generated in the fuel assembly. Ideally, the coolant should have good thermal properties, low melting and high boiling points, and a low viscosity. It must show radiation stability and low neutron absorption, be non-toxic and compatible with the fuel and structural materials. Water has the advantage of being abundant and economical. It shows good heat transfer properties and can be easily and safely handled. Control systems are used in light water reactors to control the rate of a fission reaction by absorbing neutrons and quenching the fission chain reaction. The materials suited for this application should have a high absorption cross-section, but should not transmute themselves into fissionable elements. They are found on the right side of the figure, excluding the elements uranium, plutonium, and thorium, which are fissile or fertile and used as nuclear fuel. There are different ways to control the chain reaction. The first method is to use control rods that are inserted from the bottom or the top of the core within the fuel assembly. The control rods in boiling water reactors contain boron carbide. In pressurized water reactors, they contain boron carbide or a silver indium-cadmium alloy. The control rods are connected to each other to form a control rod cluster and are distributed throughout the square lattice. A second method used in pressurized water reactors to control the rate of a fission reaction is by dissolving boric acid into the reactor water. The concentration of the dissolved boric ions is then adjusted by passing the water through an ion exchanger. The third method is to add a burnable absorber dissolved into the fuel. These materials are called neutron poisons. The control rods are used to regulate the reactor power level or bring the reactor to a quick shutdown in case of an incident. The boric acid and the burnable absorber are used for long-term reactivity control. They are compensating the effects of burn-up, in particular the build-up of neutron-absorbing fission products and the depletion of fissile material. The neutron poisons are added to the fresh fuel to lower its high reactivity. They are called burnable because their effect wears off over time as they transform into a foam that absorbs very little after capturing a neutron. Boron and gadolinium are commonly used in light water reactors. Boron is used in the form of zirconium diboride, which is applied as a thin coating on the surface of some of the uranium dioxide fuel pellets. Gadolinium is incorporated in the form of gadolinia urania fuel pellets with properties only slightly different from those of the conventional uranium dioxide pellets. The materials that we have described so far all constitute the nuclear reactor core. The other components of the pressurized water reactor are made of low carbon or low alloy steel for the reactor pressure vessel, pressurizer, steam generator, the steam lines, the turbine, and the condenser. The core structural materials and the cladding on the inside surface of the reactor pressure vessel and pressurizer are made of austenistic stainless steel. The steam generator tubes are made of a nickel-based alloy. Austenitic stainless steel and nickel-based alloys have been selected because they have low corrosion rates at high temperatures. The containment structure around the reactor pressure vessel and the steam generator is a gas-type cylinder or sphere made of carbon steel. Finally, the shield building outside the containment structure is made of concrete.
During the last 2 weeks, you learned about the fundamentals of nuclear energy and the materials involved. My name is Victor Sanchez, and today we will have a look at the most common types of nuclear reactors, the light water reactor. Let's discuss the main elements needed in a nuclear power plant. Of course, we need fuel consisting of fissile material in order to generate nuclear heat. As a result, we need a coolant to transport the heat away from the reactor core. In light water reactors, regular water is used for this purpose. The water does not only serve as a coolant, so it also acts as a neutron moderator, which slows the fission neutrons down to lower energies. Finally, the nuclear chain reaction needs to be controlled. In light water reactors, control rods are one of the ways to achieve this. In a coal-fired power plant, the heat produced from chemical energy is used to directly produce steam, which drives a turbine. The power conversion system of light water reactors is very similar to this, with few differences. For example, some types of nuclear reactors use additional water loops and a steam generator, as can be seen in the image on the right. The boiling water reactor is very similar to a fossil fuel power plant. The fission heat produces steams directly in the reactor core. The steams passes the separators, dryers, and then reach the turbine, where it expands. The enthalpy at the outlet of the core can be simply calculated by adding the inlet enthalpy and the energy added to the coolant to reach saturation and the latent heat of evaporation. The core power can be estimated by multiplying the core mass flow rate with the latent heat of evaporation. The boiling water reactor is a direct cycle circuit consisting of steam lines that connects the reactor pressure vessel to the turbine. The high pressure steam expands in the turbine and drives the generator to produce electricity. The condenser collects the water after it passes through the turbine. The water is pumped back to the reactor vessel by the feedwater pumps. Meanwhile, the water is heated to ensure that the inlet temperature is constant. In a pressurized water reactor, the single-phase coolant enters the core with a certain temperature and under high pressure. The enthalpy of the core's outlet is predicted by integrating the coolant heat capacity from its inlet temperature to its outlet temperature. The core power is estimated by multiplying the mass flow rate, the average heat capacity, and the temperature increase of the coolant along the core. A pressurized water reactor consists of a primary and secondary circuit connected by the steam generator. There, the generated heat is transferred to the secondary circuit, where steam is produced at a lower pressure. The dry steam leaves the steam generator and reaches the turbine. From this point, the pressurized water reactors and the boiling water reactors are essentially the same. In this figure, you can see an entire pressurized water reactor plant with everything from the reactor building, the turbine hall, the control room, the emergency power supply building, the chimney, etc. It's a really complex system consisting of mechanical, electrical, chemical, IC components. Finally, you see a real nuclear power plant. As example, the Biblis nuclear power plant in Germany. You see there the arrangement consisting of 2 blocks with a spherical containment, the 2 cooling towers, and so on. Thank you so much for your interest, and it would be very great to meet you again in the next video where I will present to you the fundamentals of reactor safety. Welcome back. Now that we know how power is generated in nuclear reactors, it's time to look at the safety aspects of nuclear power plants. Let's start with the overall safety goals, which are divided in technical and radiological goals. Technical goals are the control of radioactivity, the core coolability, and the confinement of radioactive material, while the radiological goals are intended to limit both the emissions of radioactive substances and the radiological exposure of the plant operators by appropriate facilities and measures. The most important question is, how can these goals be achieved when designing a nuclear reactor? Today, we will look at the following 3 methods: conservatism in design, the multi-barrier concept, and the defense in depth concept. To ensure the confinement of radioactive material, the multi-barrier concept was developed. According to this concept, the uranium dioxide pellets are enclosed by different pressure-tight physical barriers to hinder any radioactive release into the environment. These physical barriers are the fuel matrix itself, the cladding, the reactor pressure vessel, and the primary circuit, the concrete shielding, the containment building, consisting of an inner steel liner and a reinforced concrete dome. You can see all of these barriers in the figure on the screen. Now, to prevent any release of radioactive material, the integrity of the physical barriers must be assured. For this reason, the defense in depth concept was developed. Remember that under normal operation conditions, the produced heat has to be removed. Only if there is an imbalance between heat production and removal, the local degradation of the safety barriers will occur. Safety assessments are required to investigate the effects of these imbalances. To ensure the reactor can be brought to a subcritical state at all times, 2 independent, redundant, and diverse shutdown systems are required. We will have a look at these systems inside a nuclear power plant, a pressurized water reactor. One system consists of control rods made of strong neutron-absorbing materials, such as boron carbide. The second system consists of a boric acid injection system, which ensures subcriticality if a scram fails. An emergency core cooling system is used to assure the coolability of the core in case of a loss of coolant accident. It consists of passive and active systems able to inject cold water into the core. All active systems take water from the flooding tank. It is a redundant system with 4 trains, each one with a 50% capacity, meaning that only 2 systems are needed to assure core coolability. The long-term coolability is achieved by the residual heat removal system. Once the flooding tank is empty, the sump operation mode is activated automatically by the reactor control and protection systems. This means some water is injected into the core to remove the heat, and in this case, the some water will heat up continuously if nothing else happens. For this reason, the residual heat removal system consists of interconnected circuits with active pumps and heat exchangers to remove the heat from the sump water into the final heat sink, which can be a river or an ocean. The defense in depth concept is the main pillar to ensure high safety levels, and it's designed in such a way that in case of any event, the plant is led to a safe plant state. For this purpose, both facilities and measures are developed for each safety level, considering the plant states. The defense in depth concept is based on a threefold approach: conservative design principles and preventive and mitigative measures. First of all, safety levels are defined from 1 to 4. Normal operation, operational occurrences, design basis accidents, and beyond design basis accidents. Then, for each safety level, a protection goal is defined. Next, the systems foreseen to cope with the event at each safety level are listed. Finally, the procedures developed for each safety level are defined. Safety levels from 1 to 3 are purely preventive, while level 4 is mainly mitigative. Safety systems are subjected to high design requirements. The main design principles and their purpose are listed on this slide. Redundancy, for example, is helpful in case of single failure, while diversity in design is needed to improve the common cause failures. The fail-safe principle helps in case of loss of power supply, for example, for the control rods of a nuclear reactor core. Physical separation is essential against overlapping events such as flooding. Finally, automation in the nuclear power plant reduces the amount of human errors. I hope to see you in the next video where we will discuss accidents in nuclear power plants. As promised during the previous lecture, we will now have a look at how accidents in nuclear power plants are analyzed. Also, we will discuss briefly the Fukushima accident. I would like to remind you of the complexity of a nuclear power plant. It consists of many components, systems, and subsystems. During the lifetime of a plant, several events will take place, which can be caused by component failure, human errors, or a natural event. If the safety systems work as designed, the plant will be brought to a safe state. If this doesn't happen, and multiple safety systems fail, a severe accident might occur. In this case, preventive accident management will be taken. If it fails, the severe accident will progress. Finally, mitigative accident management is necessary to limit the consequences of the accident. According to the IAEA, the postulated initiating events can be classified according to the frequency of occurrence as shown in this table. At each plant state, you will have a certain probability for the occurrence of an event. Finally, you define acceptance criteria for each event category. Events which occur at any nuclear power plant of a member state are collected in national centers and pass over to the IAEA. There is an international reporting system which collects all events globally. The INES scale groups the events in 7 categories. This grouping is according to the radiological risk. This slide shows the evaluation of all events which happened in Germany over a period of 20 years. You can see that almost all events had no safety significance. In addition, for the year 1991, you see that the majority of events happened during power-up operation and during revision. Unfortunately, there is no risk-free technology. Despite safety provisions in the design and proper operation of a nuclear power plant, accidents still happen. The three biggest accidents are 3 Mile Island, Chernobyl, and Fukushima. Let's have a look at what went wrong in these cases and what the consequences were. But before we start looking at the details of each accident, let's review the method to evaluate accidents in nuclear power plants. First, a list of the major PEAs must be elaborated for each type of nuclear power plants. Then, the PIEs can be grouped based on frequency of occurrence and by phenomenology. Each safety level, event categories are defined considering safety functions and operational modes. To illustrate this, the figure shows a sketch of a pressurized water reactor primary loop. According to the phenomenological approach, you evaluate all possibilities for failures or malfunctions as listed there. These events are then evaluated with numerical simulation tools for safety demonstration purposes. More recently, the Fukushima accident was initiated by two natural events, an earthquake and the following tsunami. After the earthquake, the safety systems worked as expected to provide the short-term core coolability. However, the tsunami that followed the earthquake flooded large areas of the site and took out the residual heat removal systems, which is responsible for the long-term core cooling. Since the heat was not being properly removed from the core, it heated up, oxidized, and melted. To avoid damage to the containment building, the reactor was vented. However, due to a valve failure, a lot of hydrogen, steam, and fission products entered into the reactor building, forming critical mixtures with oxygen and causing explosions, then destroyed the reactor building. The radiological consequences of the Fukushima accident were only 10% of the ones from the Chernobyl accident, since the reactor pressure vessel was not severely damaged. However, strong contaminations have been detected to the northwest of the power plant, and many people have been evacuated and relocated. Large amounts of containment water have been released into the sea. I hope you have learned about the concepts involved when analyzing accidents in a nuclear power plant.
In order to safely operate a nuclear reactor, we need to control the reactivity. My name is Carol Lanner. During this lecture, you will learn about various effects that influence the reactivity in a nuclear power plant during operation. We will start with a short summary about the neutron life cycle. As you may recall from a previous lecture, the effective multiplication factor is the ratio between neutron production and neutron losses. If K effective is equal to 1, the reactor is critical. If it is larger than 1, it is supercritical. And if it is smaller than 1, the reactor is subcritical. This slide shows a schematic representation of the neutron life cycle, with neutrons produced by fission and neutron losses due to absorption and leakage. The reactivity is a measure of the deviation from a critical situation in the reactor and is expressed in the unit PCM. The acronym PCM stands for per cent mil. In general, the reactivity coefficient of a parameter X is defined as the change in reactivity caused by a change in the parameter X. Let's have a look at the most important reactivity coefficients. The moderator temperature coefficient is the change in reactivity due to a change in the moderator temperature. It has a negative component due to the change in water density with increasing temperature, but also a positive component due to the change in the boron concentration in the water. The net value of this coefficient should be negative for safety reasons. Because of this, there is a limitation of the boron concentration in the water during long burn-up cycles. In these cases, the addition of gadolinium oxide in some fuel rods is needed. The reactivity coefficient related to the fuel temperature is always negative because of the nuclear Doppler effect. This effect causes the resonant peaks to broaden and the resonant absorptions to increase. These increased neutron losses lead to a decrease in reactivity. The power reactivity coefficient is the addition of the previous coefficients and should be negative for safety reasons. The reactivity coefficients related to the Voigt fraction is relevant in boiling water reactors, where steam is present in the reactor core. The technical specification requirements that should be followed during the operation of the reactor are: the reactivity coefficient should be always negative. The absolute values of the coefficient should be small. Any reactivity increase should be compensated with the negative reactivity of the available control system. The negative reactivity of the control system should provide a shutdown margin of more than 3%. That means that in any situation, the control system should be able to put the core in a subcritical situation. We will now look at the effect of several fission products on the reactivity in the core. These fission products are produced during the nuclear fission reactions, along with several free neutrons. The ratio of neutrons and protons in the fission process is roughly the same as that in the uranium-235. This means the fission products are found below the stability band on the nuclear card. The graph indicates where the fission products can be found on the nuclide card. These unstable nuclei are highly radioactive and decay mainly through beta minus. These fission products, xenon-135 and samarium-149, are especially relevant due to their high absorption cross-sections. The buildup of these nuclei depends on the reactor power. The effect of these neutron absorbers are mostly seen in nuclear power plants during startup and scram and a power level change. During the operation of the reactor, the xenon-135 reaches an equilibrium concentration. After shutdown, the concentration increases due to the higher decay rate of iodine-135, which decays to xenon-135. After a while, most of the iodine is decayed, and the xenon concentration decreases to its own decay. The concentration of samarium-149 also reached an equilibrium during operation. However, after the shutdown, it behaves different than the xenon, since samarium-149 is an unstable isotope. It will not decay. The unstable nuclei promethium-149 decays to samarium-149, which leads to an increase in the concentration of samarium in the core, and a new equilibrium is reached. After a restart of the core, it takes some time for the samarium-149 to reach the previous equilibrium state. During the next lecture, we will discuss the operational control of a nuclear reactor. After seeing how the reactivity of the core is influenced by several effects, we will now look at ways of controlling the reactivity during the operation of the reactor. At the beginning of a cycle, the core has an excess in reactivity in order to compensate for its decrease due to various effects throughout its lifetime. This excess of reactivity is controlled by using control rods, soluble boron in the moderator, and gadolinium oxide inside of the fuel rods. The technical safety limits are safety restrictions that should not be violated during the operation of the reactor. We have already seen the limits on the reactivity coefficients, and we will now discuss some others. The quadrant power tilt is defined as the difference between the average power in one quadrant of the core and the average power of the full core. This value is taken from the score instrumentation and should be less than 2%. The axial offset and the axial asymmetry are two related parameters and are defined as follows. The axial offset is the relative difference in power between the upper and lower half of the core. The axial asymmetry is defined as the axial offset multiplied by the ratio of actual and nominal core power. The axial asymmetry imposes some restrictions on the power level. That means that if the asymmetry is high, the reactor power level is limited. The green area indicates the allowed combination of power and axial asymmetry. This graph shows an example of the evolution of the axial asymmetry during a power change maneuver. The power is increased from 0% to 100%, and after that, lowered to 0% again. The blue lines indicate measurements data, and the red lines indicate the results of a simulation. There is also a limit in the insertion of the control rod as a function of core power. This limit ensures that there is enough negative reactivity available in the control system to afford any unexpected increase in reactivity due to a power change. There are 4 modes to use the control systems to maintain criticality within the technical specifications. These are to use control rods and soluble boron together in order to maintain the axial asymmetry in the center of the green band, to use only control rods, to use only soluble boron, to use both systems to maintain the axial asymmetry anywhere within the green band. This slide shows a sample of an actual cycle with several maneuvers. You can see the cycle startup, several scrums, and the cycle shutdown. The goals for optimal maneuver planning are to recover power as soon as possible, to minimize borations and dilutions in the coolant in order to minimize the radioactive waste productions, and we need to stay within the technical safety limits of the reactor. During the planning, several parameters need to be considered. Among these are the core burn-up at the start of the maneuver, the shutdown time during the maneuver, the power ramp during a power maneuver, and the position of the control rods at the start of the maneuver. After these 2 lectures, you should have a general overview of the principles involved in operating a nuclear power plant.
The nuclear fuel cycle is to a large extent the uranium cycle, and therefore it is important to spend a bit of time on the chemistry of uranium before we look in the detail into the fuel cycle. My name is Thierry Wyss, and I will tell you some more about it. Uranium is the 19th second element in the periodic table, and it can be found at the far end. As you may recall from secondary school, the periodic table groups the elements according to the filling of the electron shells. Uranium belongs to the actinide series that consists of actinium and the 14 elements of the 5F block, including plutonium and thorium. In uranium, the electrons occupy 7 shells, the 5th, 6th, and 7th being partially filled due to their close energy. Uranium has 2 electrons in the 7s subshell, 1 electron in the 6d subshell, and 3 in the 5f subshell. As a result, uranium can exhibit a variety of valence states. If the 7s and the 1,6d electrons are removed, uranium has a 3+ valence state, and if then the 5f electrons are subsequently removed, a 4+, 5+, and 6+ state is obtained. The 6+ state has the radon noble gas electron configuration, which is extremely stable. The valence state of uranium has a strong influence on the physical property of the compounds. For example, the tetrafluoride is a solid salt, which just melts below 1000 degrees Celsius and boils just above 1400 degrees Celsius. The hexafluoride, in contrast, sublimes around 50 degrees Celsius to form a gas before melting. Uranium dioxide is one of the most important compounds in the nuclear fuel cycle. It is found as the mineral uraninite in nature, and it is the fuel of most nuclear reactors. Uranium dioxide is an extremely stable compound. It melts at a very high temperature of 2860 degrees Celsius. Its crystal structure is composed of regular cubic arrangement of the uranium 4+ atoms, indicated in blue, and oxygen 2- atoms in red, with uranium on the corners and the faces of the cube, and the oxygens regularly arranged inside the cube. If we zoom in on the oxygen sublattice, you can see that only half of the oxygen cubes are filled with uranium. So the uranium dioxide structure has space to accommodate other atoms, becoming non-stoichiometric. For example, extra oxygen in the empty cubes, indicated by the red plus symbol. For this to happen, 2 uranium atoms are further oxidized to 5+ in order to keep electron neutrality. The oxygen over uranium ratio will thus become larger than 2, which is called hyperstoichiometric. In the same way, uranium can be reduced to +3, accompanied by the creation of a vacant oxygen position in the crystal lattice, indicated by the black square, and so forms a hypostoichiometric compound. This means that UO2 can have a very large deviation from the stoichiometric composition at high temperature, which has a significant effect on its properties. The valence state of uranium also has an impact on the dissolution behavior. The tetravalent uranium compounds are very insoluble, and UO2 can only be brought into solution with extremely strong acids, such as a concentrated nitric acid. The solubility can be well demonstrated by a so-called EH-pH diagram that shows the stability domains as a function of the acidity, the pH, and the electron affinity of the solution, the EH. In the area between the 2 red dotted lines, showing the stability domain of water, there are 2 main fields, the solid uranium dioxide, indicated by the black field, and a variety of hexavalent uranium aqueous species that are grouped in the blue field. As you can see now, in most of waters on the surface of the Earth, hexavalent is stable in solution. Uranium dioxide is only stable in water that are isolated from atmosphere. The hexavalent uranium forms a very stable molecule in solution, the so-called uranyl oxocation. This is a linear molecule with a very strong triple bond between uranium and oxygen. Since the space around the positively charged uranium is free, all the ligand can bind to the molecule in the equatorial plane. Here you can see the uranyl nitride molecule, for example. In this molecule, 2 nitride ligands bind to the uranyl, with 2 oxygen each, giving the uranium a 6-fold octahedral coordination. When the uranium precipitates from the solution, it forms uranyl salts with the same octahedral structure around the uranium. All in all, we can say that the nuclear fuel cycle has very much to do with the conversion between chemical forms of uranium in order to purify, enrich, fabricate, and dispose the fuel. You can see the most important compounds here. In the next lecture, we will elaborate on their role in the nuclear fuel cycle. We have just learned about the physico-chemical properties of uranium, and we'll see how it is processed, starting from the mining to its fabrication to a fuel pellet that will be used in a nuclear reactor. The front end of the nuclear fuel cycle is the collective term for all the processes that are indicated in yellow in this slide. Uranium is a rare element in the Earth. It is concentrated in the continental crust of the Earth at an average concentration of about 1 part per million, which is 500 times higher than, for example, gold. This concentration is too low for mining, and only deposits in which the uranium is further concentrated are of interest. There is a wide range of concentrations in the uranium ores, going from about 500 ppm to a few tenths of percent, as well as the deposit size. Whether it is interesting to unveil and mine the ores depends on the costs, or the other mining products, environmental conditions, among others. In the graph, you can see 2 extremes: the Olympic Dam mine in Australia with a low uranium concentration, and Cigar Lake in Canada, a very high concentrated ore, both representing enormous quantities. Chemistry plays an important role in the concentration of uranium in the ores. We have learned in the previous lecture that uranium can be dissolved easily in the waters in contact with the atmosphere, and dissolution precipitation processes are therefore one of the main ore concentration mechanisms. For example, the figure shows how atmospheric waters enters a sandstone formation where it dissolves the uranium. When this solution comes in contact with an environment with a different EH, for example, because that environment contains divalent iron such as iron sulfide, the uranium can be reduced back and tetravalent uranium precipitates in concentrated form. The mining technique can thus be very different. Classical underground mining is one expensive and is only interesting for high-grade ores. Cigar Lake is one of the most striking examples. Open pit mining is less costly and can thus be used for lower-grade ores. An increasingly popular method is in-situ leaching, in which an oxidizing solution can bring poorly soluble uranium into solution, as we learned in the previous video, is pumped into and circulated through the ore body to dissolve the uranium. The Olympic Dam mine is the most well-known example of this. In case of mining, the uranium must be extracted from the ore. This is done by crushing the mine rock and mixing with an acid solution to leach the uranium. However, not only uranium, but also other soluble elements are leached into the solution. In the next step, the uranium is therefore selectively extracted from the solution, either by ion exchange or solvent extraction. It is then precipitated by adding ammonium hydroxide to the solution, forming ammonium diuranate, which is then dried to give yellow cake, a product mainly made of U3O8. As you have learned in a previous presentation, the uranium-235 concentration in natural uranium is too low for use in a light water reactor and must be increased between 4 to 5% for a few cycle lengths of 4 years. This is nowadays mainly done by use of ultracentrifuges that make use of the difference of the centrifugal forces on gaseous molecules of different mass. In this process, uranium hexafluoride is used. Therefore, the next step in the fuel cycle is the conversion of the yellow cake to UF6. This is possible because UF6 is a gas near room temperature. It contains only one uranium atom, and fluorine has only one isotope, thus not changing the mass difference of 3. UF6 is produced by dissolving the yellow cake to refine it from decay products to yield UO3, which is reduced to UO2 with hydrogen. This UO2 is then reacted with gaseous hydrogen fluoride to form UF4, which is subsequently reacted with fluorine gas to yield UF6, which is stored as a slightly pressurized liquid in special tanks that can be transported to the enrichment plants. In the centrifuge, centrifugal forces push the heavier uranium-238 fluoride closer to the wall of the rotor than the lighter uranium-235 fluoride. The gas closer to the wall becomes depleted in uranium-235, whereas the gas nearer the rotor axis is slightly enriched in uranium-235. The efficiency of one centrifuge is very small, and therefore many are combined in one stage, and the stages are placed in cascades in which the yield is optimized. The UF6 must now be converted back to UO2. This is done by reacting the UF6 with gaseous water and ammonia to form ammonium diuranate. This is then dried and reduced in hydrogen to UO2. The product is then milled to get a uniform powder quality. UO2 pellets are fabricated from the powder by compacting it in a biaxial press to a pellet that has a density of about 50% of the theoretical one. This density is not sufficient, and by sintering at 1600 degrees Celsius, this density can be increased to close to 95%. The pellets have a special shape with a dish and a chamfer, and in the next video we will learn what their function is and why the density is so important. In this presentation, we will stress the extreme conditions which affect the properties and behavior of the fuel during irradiation. So far, we have discussed the front end of the nuclear fuel cycle, and here we will focus on the next step, which is the irradiation in a reactor, and discuss the consequences on the fuel behavior. The fuel is exposed to very high levels of energetic radiation. It has a high temperature as a result of the heat that is produced in the fission process. It has a changing chemical composition because of the fission product formed, and its cladding is exposed to high temperature water. We will look in this video how this affects the integrity and life of the fuel. The fission process creates two fission products and releases at the same time about 200 megaelectron-volt energy. Most of the energy is transferred as a kinetic energy to the fission products, which does have the capacity to knock on atoms from the crystal lattice of UO2, creating vacant position and displacing atoms to non-regular interstitial positions. A heavy fission product, such as barium-144, creates about 60,000 defects. A light one, like krypton-89, about 40,000. Many of these defects heal again quickly because of the temperature of the fuel, but some remain and even form clusters or extended defects. In this molecular dynamic simulation, the recall atom is the larger represented gray sphere and displaces the uranium in orange and oxygen in blue from the regular lattice positions. While most of the defects are quasi-instantaneously healed, some lattice defects are left at the end of the cascade. As already discussed in a previous presentation, a wide range of fission products is formed, and they double the number of original uranium atoms fissioned. These fission products are foreign, and most of them do not fit in the crystal lattice of UO2 and form secondary phases such as oxide and metallic precipitates and gases that collect in pores and voids. These secondary phases can be observed by electron microscopy analysis. The gas bubbles with noble gases xenon and krypton, and spherical metallic precipitate containing noble metals. These new phases also contribute to the expansion of the fuel pellets. The temperature in the pellet is depending on two parameters: the amount of heat produced, the linear heat rate, and thermal conductivity of the fuel materials, as this simplified formula shows. As a result of the relatively poor thermal conductivity of UO2, the temperature gradient is steep, about 800 degrees Celsius between the center and the rim of the pellet. Since the gap between the pellet and the cladding is filled with helium, which also poorly conducts the heat, there is an additional temperature step close to the cladding. Because of this temperature gradient, the pellet has a different thermal expansion across the radius, and as a result of the stress, it starts to deform and fracture. As a result of the deformation, the top and bottom edges move outward and can eventually touch the cladding, leading to local stress. To avoid this, the pellet general have a dish and a chamfer. This can be very nicely seen in this picture of irradiated fuel of low and high burnup, the low burnup fuel still having an open dish, whereas it is closed in the high burnup fuel. As a result of the expansion of the pellet and the inward creep of the zirconium alloy cladding under the influence of radiation, the gap between the pellet and the cladding closes, and with increasing expansion of the fuel pellet with burnup, the pellets start to exert a mechanical stress on the cladding. This can be a possible cause for cladding failure, and this is a possible life-limiting factor for fuel pins. Another limiting factor is the corrosion and degradation of the cladding from the water side. This high-temperature pressurized water is corrosive towards the zirconium alloy, and a zirconium oxide layer is formed. In a chemical reaction, the metal binds the oxygen from the water and sets free hydrogen, which diffuses into the metal and forms zirconium hydride, which can be seen as worm-like precipitate in the photograph. The oxide layer reduces the thickness of the cladding, and the hydride affects the mechanical strength of the cladding. The diffusion of oxygen through the zirconium oxide layer to the metal oxide interface is the rate determining step for the oxidation, and this is an Arrhenius type process. Thus, the reaction slows down asymptotically. However, the zirconium oxide layer is brittle and easily fractures or breaks off, a result of which the reaction speed increases again. So the lifetime of the fuel elements is limited to about 4 years, after which the composition of the fuel has changed significantly from pure UO2 to about a material with about 6 to 8% newly formed element, fission products, and activation products.
Now we will discuss different fuel cycle options. So far we have discussed all steps in an open or once-through fuel cycle, from mining till final geological disposal. It is called an open fuel cycle as there is no link back to the fuel cycle. But the cycle can be closed when the spent nuclear fuel is not regarded as waste, but as a valuable energy source. If we look back at the composition of spent nuclear fuel, it shows that more than 96% of it consists of uranium and plutonium. Comparing the isotopic composition of uranium before and after irradiation, we see that in this example, 3/4 of the fissile uranium-235 is consumed. Isotopic composition of plutonium shows that the majority of it is fissile, plutonium-239 and plutonium-241. This means that spent nuclear fuel still contains valuable fissile material for energy production. The aim of reprocessing the spent nuclear fuel is to recover uranium and plutonium so that it can be recycled as fresh fuel. Doing so, the fuel cycle is closed. The new fuel will be a mixed oxide fuel, a MOX fuel, as it is a mixture of uranium dioxide and plutonium dioxide. The main fissile nuclide in MOX is plutonium-239, so that depleted uranium can be used for the uranium dioxide part of it. MOX fuel is being used in commercial light water reactors, for example, in France, Belgium, and Japan. Reprocessing includes the following major steps. First, a mechanical process separates most of the spent nuclear fuel from the assemblies and claddings. Then the spent nuclear fuel is dissolved in nitric acid with careful treatment of the off-gases and residues. In the following step, a solvent extraction process separates uranium and plutonium from the fission products and minor actinides. And the uranium and plutonium nitrates are then converted into uranium and plutonium dioxides. And finally, the waste, mostly high-level waste, containing the fission products and minor actinides, has to be handled appropriately. The most used extraction process, called PUREX, which stands for plutonium uranium extraction, is based on liquid-liquid extraction principles, where a substance is extracted from one liquid into another immiscible liquid phase. In this case, uranium and plutonium are extracted from the aqueous nitric acid phase to an organic phase, kerosene, containing TBP, tributyl phosphate, as the extracting molecule. On an industrial scale, this process is performed by a series of centrifugal contactors, one after the other, repeating the process, so that at the end, high extraction efficiencies are reached. Out of the organic phase, plutonium and uranium can be separately back-extracted to the aqueous phase. There too, plutonium-4 is reduced to plutonium-3 by the addition of uranium-4 nitrate, or iron 2+. Plutonium-3 is then back-extracted to the aqueous phase. In order to back-extract uranium out of the organic phase, the aqueous phase is changed to diluted nitric acid. Uranium is now more stable in the aqueous phase and transfers back to it. Plant-scale performances of the Purex process reach recoveries of uranium and plutonium of 99.9%. Reprocessing creates some high-level waste, like the aqueous fraction containing fission products and minor actinides, which needs to be disposed of in an appropriate way. There too, the high-level waste is first concentrated and calcined. Then it is mixed with borosilicate glass frit and heated at 1100 degrees Celsius. And this liquid glass mixture is poured into stainless steel canisters, and after cooling down, letting the glass solidify, the canister is welded shut and can be transported to the interim storage. Also, more advanced fuel cycle options are being studied. In partitioning and transmutation, PNT, the aim is to reduce the long-term radiotoxicity of the high-level waste from spent nuclear fuel, compared to the same amount of natural uranium, from more than 100,000 years to 1,000 years, or even less. Scenario studies show that this can be achieved by not only recycling uranium and plutonium, but also the other minor actinides. You might remember from the previous lecture that the actinides are the main contributors to the long-term radiotoxicity of the final disposal site. There are two distinctive parts in PNT. The partitioning regards the separation of the minor actinides after the Purex process, and the transmutation regards the burning of the long-lived plutonium and minor actinides into shorter-lived nuclides. For an efficient transmutation, a thermal neutron spectrum is not well suited. You need a fast neutron spectrum. For a successful PNT scenario, we need separation efficiencies of more than 99.9% in combination with fast reactors for the multiple recycling of plutonium and minor actinides with transmutation efficiencies of 10–20%. The choice for an open or closed fuel cycle differs by country. Countries like Sweden, Finland, Germany, USA, Canada have chosen for the open fuel cycle. Other countries like France, UK, Japan, China, Russia for a closed fuel cycle. Countries like Argentina, Brazil, and South Korea, they did not decide yet. Research in more advanced PNT options are ongoing in many countries. An excellent source of actual information for the nuclear activities of many countries is the document Country Nuclear Power Profiles by the International Atomic Energy Agency. That's it. Now you have a flavor of what is the nuclear fuel cycle all about. Hi everybody. So far we have been digging for uranium, enriched it in fissile uranium-235, produced nuclear fuel out of it, and used this fuel in a nuclear reactor. My name is Stefan van Winkel, and I will tell you about the next stages in the nuclear fuel cycle. I will discuss how to responsibly deal with the spent fuel, the fuel after irradiation, from the cooling pool to the interim storage, and from conditioning to the final geological disposal. Let's look again at the information about the quantities of the different constituents of a typical spent fuel. Having started with 1,000 kilogram uranium in the fresh fuel, we have still got 950 kilograms uranium left in the spent fuel. Through neutron capture, 11 kilograms has been transformed into mainly plutonium plus some minor actinides. 39 kilogram fuel underwent fission, resulting in the fission products. You might remember the curve of the fission yields from a lecture in the first week. Well, the quantities of different fission products reflect this figure perfectly. with 16 kilogram lighter fission products and 23 kilograms heavier fission products. Many of these fission products are radioactive and so decaying faster or slower depending on the respective half-lives. The characteristics of the spent nuclear fuel define how we can deal with it in a safe and responsible way. Spent fuel still contains fissile material, so we have to store it in a configuration that guarantees a subcritical system. That is why the spent nuclear fuel is stored in special racks, with eventually the use of neutron absorbers, for example boron-10. The spent nuclear fuel is highly radioactive, so we have to shield it. And the decay heat makes the spent nuclear fuel hot, so we have to store it in a cooling pool. A typical cooling pool is about 12 meters deep, so that the spent nuclear fuel is 8 meters below surface. The water functions as radiation shield and as coolant. A water cooling circuit keeps the pool temperature typically below 35 degrees Celsius. Water level and temperature are carefully monitored, and hydrogen detectors near the pool check for radiolysis of the water. Spent nuclear fuel normally remains in a cooling pool for several years. Some countries like Sweden and Slovakia, they keep spent nuclear fuel in such wet storage conditions. Other countries put the spent nuclear fuel after sufficient wet cooling in dry storage containers. Whole spent nuclear fuel assemblies are placed in a welded or bolted canister under inert atmosphere. The canister is placed in a storage cask or in a transportation cask or in a dual-purpose cask, combining both purposes. Dry storage can be vertical or horizontal, can be outdoors or indoors, at the reactor site or at centralized locations. Surface storage is a temporary solution which cannot replace the need for a geological repository. Before final disposal, the spent nuclear fuel will need to be conditioned. This means it has to be repackaged in a disposal container. Such disposal container should be corrosion resistant, withstand internal and external pressures, and be heat conducting so it can act as a safety barrier. The goal of the final disposal is to isolate radioactive waste from the environment through a series of engineered and natural barriers. In the case of spent nuclear fuel, you have the fuel pellet as a waste form inside the cladding, the fuel pins as assemblies inside the canister surrounded by absorbing backfill material, and all this in a geologically very stable host rock deeply underground. Different countries have got different geological conditions, so different host rocks are being studied for their repository properties. For example, hard rock in Sweden and Finland, volcanic rock in the USA, salt rock in Germany and the USA, and clay in France, Belgium, and Switzerland. The choices of the best canister and backfill materials depend very much on the site-specific host rock conditions. Safety studies include the scenario that in the long term, groundwater might finally reach the spent nuclear fuel, despite all barriers. For the consequences this might have on the fuel matrix, we have to look back at lecture 4.2. You might remember from that lecture that the solubility of uranium-4 is much lower than the solubility of uranium-6, meaning that reducing conditions and low values for EH and dissolved oxygen in water are favorable for limiting the dissolution of the uranium matrix in spent nuclear fuel. In the long term, all short-lived radionuclides have decayed to stable nuclides, and only the long-lived radionuclides will remain. For spent nuclear fuel, the most important remaining radioactive nuclides after 1,000 years in the geological disposal site are the actinides, such as plutonium-239 and plutonium-240. The fission products like technetium-99 and cesium-135, and activation products like carbon-14 and chlorine-36. Scenario studies have shown that the most problematic nuclides of this list are cesium, iodine, and chlorine due to their high mobility. If you now think that we have finished with the nuclear fuel cycle, sorry, but you're mistaken. There exist alternative ways to deal with spent nuclear fuel. Check it out in our next video.
Welcome to the 5th week of the course. We are glad to see you're back. Today's topic is the life cycle assessment of nuclear energy. My name is Sara Boarind and I will present you the key concept of this topic. A life cycle assessment encompasses all the phases of a product's lifetime and evaluates its impact on resource utilization and its economic and social effects. During this lecture, some concepts of nuclear power generation life cycle assessment will be discussed. The economics of nuclear power will be treated in the next lecture. Today, about 17% of all electricity in the world is generated in nuclear power plants. A pressurized water reactor with a burn-up of 65,000 megawatt-day per ton requires 145 tons of natural uranium for 1 year of operation. Fast breeder reactors will improve the fissile material utilization and thereby will reduce the consumption rate. The global annual uranium requirements are projected to rise from 68,000 tons in 2016 to between 72,000 and 122,000 tons by 2035. Uranium resources are classified depending on the level of geological confidence and on the extraction cost category. Non-recoverable resources with a price lower than $130 per kilogram of uranium are estimated at 5.9 million tons and will cover our current usage for about 90 years. Undiscovered resources are expected to exist based on geological knowledge of previously discovered deposits and regional geological mapping, but require significant amounts of exploration to confirm their existence and define grades and tonnages. In the 1990s, large amounts of weapons-grade uranium and plutonium came to the civil market due to several treaties between the United States and Russia in order to reduce their nuclear arsenals. This material has since been used to fuel nuclear power stations. You have already seen in last week's lectures that part of the spent nuclear fuel can be reprocessed to produce fresh fuel in a closed fuel cycle. However, reprocessing is only one of the ways we can use to increase the efficiency of the nuclear fuel. Other ways are increasing the enrichment of the fuel on the front end of the cycle, or increasing the burn-up by using the fuel for longer periods of time in the reactor. Mining and milling produce the so-called yellow cake, where natural uranium contains 0.7% concentration of uranium-235. This concentration needs to be increased to 3.5% for use as reactor fuel. The enrichment is based on the physical separation of isotopes by means of different technologies. The waste from these processes is depleted uranium. After enrichment, the uranium oxide is pressed into pellets. Radioactive waste is classified according to the concentration of radionuclides and their respective half-lives. The main component in volume is the low-level waste. It comes from nuclear plant operation and typically consists of contaminated protective shoe covers and clothing, mops, filters, reactor water residues, and tools. Big volumes of low-level waste may come from nuclear power plant dismantling, demolished material such as concrete, plaster, bricks, metal, valves, and piping. Intermediate-level waste typically comprises resin, chemical sludge, and metal fuel cladding. High-level waste mainly consists of the spent fuel. This picture gives you an idea of volumes of waste products in spent fuel. 15.6 tons of enriched uranium are needed to fuel a generic 1 gigawatt pressurized water reactor. This means about 1.8 ton per terawatt hour produced. Plutonium represents slightly less than 1% in weight of the spent fuel, and the other transuranic elements even less, but they are the major cause of long-term radiotoxicity of the spent fuel. After on-site storage for tens of years, the spent fuel is sent to a reprocessing facility or directly to a final disposal.
Fuel reprocessing reduces the radiotoxicity in spent fuel. Recycled plutonium is used in the fabrication of MOX fuel for light water reactor. Partitioning and transmutation reduces the radiological hazard in terms of magnitude and duration by eliminating long-lived heat-producing actinides and reducing the quantities of the fissile and fertile radionuclides that present proliferation concerns. Final disposal options for high-level waste are geological repositories. The fuel is confined in special canisters able to reject residual heat and stored in tunnels about 500 meters below the surface. Studies on geological repositories for high-level waste are ongoing in Sweden, Switzerland, USA, France, Canada. In Finland, a geological final repository is currently under construction. You have seen my lecture about the resources and processes involved over the lifetime of a nuclear power plant. It is now time to discuss the economics of nuclear energy production. I am Sara Boarin. Let's dive in. We will start with some key economic indicators. The levelized cost of electricity is the unit electricity generation cost, and it is widely used for comparing costs of different power technologies. The lower the LCOE, the better are the project economics. The net present value is the total value generated by a nuclear power plant during its entire lifetime. The internal rate of return is the profitability ratio of the nuclear power plant project. Cash flows generated by the project are compared to the capital investment. The payback time is the time when cumulated earnings from the nuclear power plant equal the cumulated costs. In order to calculate the NPV, all the cash flows, both positive and negative, are considered, discounted and cumulated. The internal rate of return is the interest rate that breaks even the NPV. In the discounted cash flow approach, LCOE may be calculated as the electricity price that breaks even the NPV. Here, nuclear power plant 1 in red has better economics than plant 2 in blue, since the cost of a unit of energy is lower. A higher discount rate decreases the NPV and increases the LCOE. The discount rate is the cost of capital that represents the remuneration rate required by investors. It reflects the risk perception by investors. When future cash flows are less certain, investors ask for a higher remuneration rate. The project risk increases with longer payback times. Capital costs, which include construction and interest, represent the predominant share of the LCOE from a nuclear plant. Almost all the components of the nuclear LCOE are fixed, except for fuel cost and few consumables used in operation and maintenance. The LCOE varies significantly by country, since a relevant part of the construction cost is country-specific: salary, nuclear safety regulation, local supply chain, and so on. As said, higher interest rate increases the LCOE. You can see the effect of the interest rate in the figure on the right. The LCOE may be calculated without a DCF approach, as the lump sum of all the cost components annualized: construction, operation, decontamination and decommissioning, fuel. A constant equivalent cost annuity is calculated and divided by an average annual electricity output in megawatt hours. The LCOE can be viewed as the minimum constant electricity price that covers all the costs and breaks even the project. In this case, the cost of capital and the decontamination and decommissioning are accounted in the construction cost component. Construction costs are sunk costs for investors and have to be recovered by means of the sale of the electricity produced. Any factor that may compromise the revenue stream is a risk factor. As an example, plant availability, market price volatility, electricity demand, and so on. The revenue stream has to be maximized, and this pushes towards the maximization of the capacity factor. This is why nuclear power plants are said to be price takers. Nuclear power does not play a role in setting the price on the electricity market, since it has to produce power at full regime and cannot play on flexibility like generation technologies that have predominantly variable costs. Here, a sensitivity analysis on the LCOE is provided. Each input is increased and decreased by 50%, and its impact on the LCOE is calculated separately. The percentage change in the LCOE is represented in the graphs on the screen. The most sensitive parameter is the financial interest rate. Construction cost overruns and construction lead time are major concerns, since these can seriously undermine the nuclear project economics by deteriorating the profitability and increasing the LCOE. The Generation 4 International Forum has defined a comprehensive code of account of total capital investment costs. That is a cost breakdown system. According to this code, half of the total construction costs are capitalized direct costs that include equipment, on-site direct labor, and commodities such as wire and concrete. Main components of direct costs are civil and reactor equipment, including the steam generator and turbine equipment. Total direct costs may also be divided into nuclear island costs, some 40%, and balance of plant, which includes all the residual systems and equipment. The economy of scales apply to capital cost of all industries and even to single pieces of equipment with different specific coefficient F in the formula. The principle is as follows. If the plant size increases in terms of output, total cost increases less than proportionally with respect to the plant output. Therefore, unit construction cost is expected to be lower for a large plant compared to a smaller one, instead of being constant. Economy of scale significantly reduces the expected total cost of a large-sized plant. The effect of economy of scale is relevant in the nuclear industry, where capital construction costs are very high. This is the reason that push towards the maximization of the size of nuclear power plants throughout history. However, could there be a minimum in the economy of scale curve, a size beyond which this economy of scale starts to apply? For now, this is still an open question. The fuel cycle costs are divided in the front end, containing the uranium supply, conversion, enrichment, and fuel fabrication, and the back end, which contains reprocessing, conditioning, and final geological disposal. They vary widely with the fuel cycle strategy, one through or reprocessing. Disposal costs depend on geological conditions and on the repository features, and until now, no industrial reference costs are available on this topic. Normally, a decommissioning and decontamination sinking fund is established during the plant's operating lifetime that sometimes can be invested in high-grade tax-free bonds to accumulate the funds necessary for decommissioning. The sinking fund formula indicated here can be used to calculate the annual payment to the D&D fund. At present, no universally accepted standard is established for developing decommissioning cost estimates, which vary depending on the D&D strategy, the scope of activity, the final state of the site, the plant type, and so on. Due to the actualization effect on long-term expenses, the D&D component in the LCOE is negligible.
This video will give you an introduction to nuclear security. When we speak about nuclear security, we are referring to physically securing nuclear materials, facilities and related activities, but also sensitive information, computers, and personnel. In this video, we will focus on nuclear security specifically applied to the nuclear materials, but the concept that will be presented can easily be transposed to the remaining aspects. 4 main items will be discussed in this video. The first item is related to the need for nuclear security. In the second one, we will discuss the nuclear facilities and related activities that need to be protected. In the following item, we will present how a national nuclear security regime should be implemented. And last but not least, we will see the main principles for the physical protection of nuclear material. The main objectives of nuclear security are to protect people, properties, society, and the environment. In an ideal world, where no threat would exist, there would be no need for security. Only safety would matter in that case. Unfortunately, this is not our world, and threats exist. What are the threats that the nuclear security should protect against? It should protect against malicious acts by an adversary. These acts can be unauthorized removal with the intent to construct a nuclear explosive device, unauthorized removal which could lead to subsequent dispersal, or sabotage. In this video, we will limit ourselves to the protection against the risk of a malicious act with the intent to construct a nuclear explosive device. The two other risks will need different specific security measures, but the concept behind are similar. I referred earlier to nuclear facilities and associated activities. What do we consider in there? It covers the full life cycle of nuclear material. The figure here represents the nuclear fuel cycle. As we can see, the nuclear fuel is produced, used, stored, or recycled during its life. At each related facility, the material should be protected by security measures. This is also the case when the material is transported from one facility to another. Nuclear security is based on different international conventions. One major convention for nuclear security is the Convention on the Physical Protection of Nuclear Material of the United Nations, which obliges the states to protect their nuclear material. The International Atomic Energy Agency has developed over the years guideline documents in the nuclear security series. These documents can be used by member states as a basis for their national, legal and regulatory framework. Each state is responsible for the physical protection of its nuclear material and associated activities by building an adapted national regime for physical protection. The regime for physical protection should contain a legal framework, define clear responsibilities during the full life cycle of the nuclear materials, define the competent authority with regard to the physical protection, and contain a regulatory structure. The malicious use of the nuclear material will have different potential consequences depending on the radioisotopes contained in the material and the quantity of material. According to this, the International Atomic Energy Agency has categorized the nuclear facilities materials in three different categories. Category 3 is the one having the lowest consequences, whereas Category 1 has the highest consequences. Due to the fact that these different categories of nuclear materials have different consequences, the security measures to be applied are different from one category to another, with the most stringent for Category 1. This will lead to different security zones, resulting in what we call a graded approach. Nuclear material in Category 3 should be contained in a limited access area, which is designed with specific security measures. The nuclear material in Category 2 should be contained in a protected area, which needs in turn to be contained in a limited access area. The protected area is designed with increased security measures. Finally, nuclear material in Category 1 should be contained in an inner area, which needs to be contained in a protected area, which is already contained in a limited access area. The inner area has the most stringent security measures. This is what we call the defense in-depth approach. The physical protection system, which is an integrated set of physical protection measures intended to prevent the completion of a malicious act, is based on a four-step approach. The first step is the deterrence of malicious persons by monitoring the threat level, counter-observing, and the use of deterrence equipment, such as a fence and other rather visible security measures. If there is an attack, the second step will enter into action, which is the detection and assessment of potentially malicious or unauthorized acts with, for example, a CCTV camera. After the assessment, the response will intervene in case of an actual event. The last step, and certainly not the least, is the delay step, which is performed through different mechanical barriers installed to protect each security zone of the nuclear facility, allowing sufficient time for the response to neutralize the attack. These four steps are not only achieved by equipment, but also by strict procedures, computer security, information protection, and personnel security measures. The security system of a facility is not only dependent on the measures that are applied, but also on the people applying and being aware of the security measures and the potential consequences of the malicious use of nuclear material. This is called the security culture of the facility. Thank you for your attention.
When we discuss nuclear energy, often three risks are mentioned related to the use of nuclear energy. The risk of a nuclear accident, the risk of nuclear waste with long half-life, and the risk of proliferation of nuclear weapons. Nuclear safeguards focuses on this last aspect of nuclear non-proliferation. Let's look to what safeguards really is, why it has been established, where and how it is implemented, and the basic principles on which its implementation is based. Safeguards, security and safety are often confused and were in the past often treated separately. Presently, we use the 3S concept, safety, security and safeguards, to integrate them in a more holistic approach. Nuclear safety is the prevention of accidents in nuclear installations that have unintentional causes, like natural hazards, equipment malfunctioning, or human errors. An important aspect of nuclear safety is the mitigation of the consequences of such an accident. Nuclear security focuses on the prevention of intentional human acts, for instance, to sabotage a nuclear installation or steal nuclear material. Again, mitigation of the consequences of such acts are an important aspect. Nuclear safeguards are international inspections that verify that states do not manufacture nuclear weapons from nuclear material in their peaceful activities. The legal basis for international safeguards inspections are the Non-Proliferation Treaty, the additional protocol to the Non-Proliferation Treaty, and for the EU countries, the Euratom Treaty, which is part of the EC treaties. The Non-Proliferation Treaty and safeguards inspections were established at the end of the 60s of last century. This was due to the concern that more and more countries seemed to want to acquire nuclear technology for the manufacture of nuclear weapons. To distinguish between military and peaceful use of nuclear energy, the Non-Proliferation Treaty framework was created. Not only to prevent the horizontal spread of nuclear weapons, but also to facilitate the trade of peaceful nuclear technology. Safeguards inspections are conducted by the International Atomic Energy Agency in all states that are part of the Non-Proliferation Treaty and that possess nuclear material. All nuclear material in possession of a state is subject to nuclear inspections. Also, the design of nuclear installations is inspected. The purpose of these inspections is to verify that all these activities cannot be misused for military or undeclared purposes. Safeguards inspections in the framework of the additional protocol also look to indications that states conduct undeclared activities or produce undeclared nuclear material. How do we perform these safeguards inspections? For instance, with visual inspections, we verify ID numbers on nuclear fuel rods. With seals and cameras, we make sure that the time between two inspections, nuclear material has not been moved or touched. With measurements of radioactivity or mass, to verify that the material has not been changed or diverted. And with other types of measurement, like calorimetry, to measure whether the heat output of plutonium, for instance, remained the same. This quote comes from a document called INCIRC 153. This document describes the implementation of safeguards inspections in states. Important elements are timely detection, significant quantity, and risk of early detection. The timely detection concept is used to determine how often safeguards inspections should take place. For material that can be used directly in a nuclear weapon, like plutonium or high-enriched uranium, this timeliness criterion for timely detection is defined as 1 month. For less strategic materials, like low-enriched uranium, this is 1 year. The reason for this 1 year is that it will take quite some time to make weapon-usable material out of low-enriched uranium. Significant quantity determines how much material should be verified and how much material should be taken away in order to provoke an alarm. For plutonium, it is defined as 8 kilograms, while for highly enriched uranium, it is 25 kilograms. The probability to detect a diversion depends on the strategic value of the material. For high-enriched uranium and plutonium, the detection probability is high, like 90%, while for low-enriched uranium it is set on the level of 50%. The more often you inspect, the higher the detection probability will be. The general purpose of the safeguard system is, on the one hand, to deter a state from proliferating, and on the other hand, to provide assurance to the international community that all state parties behave in a responsible way. I hope that I have provided you with a first insight on what Safeguards is, and hope to see you again in one of the more extensive courses that we provide. Thank you.
Hello, I'm Pierre Kokkerels and working at the European Commission's Joint Research Centre. My lecture will cover a topic that receives more and more attention today, nuclear decommissioning. I will explain you what decommissioning is, why it is important, and what the main challenges are for Europe. When we speak about nuclear decommissioning, we mean basically all the actions from ceasing the operation of a nuclear installation, the preparation of a plan and license, the evacuation of the residual fuel, the decontamination and dismantling, the segregation of the various types of waste, the radiological survey of the buildings, and their demolishment if they are not reused, until the final release of the site from regulatory control. Experiences with decommissioning date from the earliest stages of the nuclear history, which as example the shipping port reactor, decommissioned in only 5 years in the 1980s. But the practice has gained importance over the last decades. Several EU countries have decided to decommission their oldest facilities. Some first pilot projects were managed under research programs like the BR3 reactor in Belgium. But currently, the activity has grown and reached an industrial scale. A map of Europe shows that about 1/3 of the nuclear power reactors are currently shut down. The situation is variable between the different countries. The complete work, from the end of operation until the final release from regulatory control, is a long-term process, which can exceed easily 10 to 20 years for large installations. And this explains why today in Europe, despite a growing know-how, only few major nuclear installations have been fully decommissioned. There are, in my opinion, 4 principal reasons why we should progress with decommissioning. The first motivation is the respect of ethical principles. Liabilities from past activities may result over time in unacceptable environmental, safety and security risks. Equity requires that the generation which incurs the liabilities minimizes the burden for future generations. Liabilities should be managed in such a way that potential future impacts are kept at a level that is acceptable both economically and in terms of safety. A second reason is that timely implementation of decommissioning projects will increase societal confidence in the capability to deal with the long-term consequences of nuclear power, which could facilitate public acceptance for future industrial projects. Complementary to these ethical and societal considerations, there is also an important economic driver for an early implementation of decommissioning programs. Investments may spur development of new businesses. And conversely, delaying decommissioning projects may be costly due to the potential degradation of structures, the spread of contamination, and the loss of knowledge. And the fourth reason is the necessity to comply with the international arrangements. Environmental issues can have a transboundary impact on neighboring countries. and the arrangements made will help to build trust between neighboring countries. Decommissioning is important, but it is not an easy business, and European society faces several challenges. First of all, countries must have a national policy and a supporting framework established to deal with their liabilities. In this sense, the European Directive on the Responsible and Safe Management of Spent Fuel and Radioactive Waste from 2011 imposes to all EU member states to develop a national programme and to report periodically to the European Commission on evolutions. Clearly, decommissioning programmes must be financed, and EU countries are obliged to ensure reserves. In some countries, they are foreseen by the utilities, and in others, they are counted by a national fund. And the decommissioning cost estimates for one nuclear power reactor range from €0.5 to €2 billion. But expected costs can be for some installations much higher. For instance, over £100 billion estimated for the decommissioning of the whole Sellafield site in the UK. Finally, the availability of qualified experts, qualified personnel is essential and is probably the most critical issue to deal with. European nuclear sector faces increasing difficulty in recruiting staff with the required expertise. It can be expected that the decommissioning industry will face an even more significant shortage of competent personnel. At first glance, a career in decommissioning seems not particularly exciting. Clearing, cleaning and demolishing of facilities is perceived as less attractive than constructing something new. However, the finality of decommissioning is environmental plus economic valuation. Decommissioning can be challenging due to the variety of issues to be resolved, requiring a mastery of a diverse set of competences. The experience shared by young professionals working today already in decommissioning shows that the job offers many career possibilities that make it particularly attractive and secure. With this overview, I hope to have raised your interest for this emerging activity, and I thank you for your attention.
What will be the new nuclear fission technology we will use in the future? A possible answer to this question is represented by two liquid metal fast breeder reactors, the sodium and the lead-cooled fast reactor. These two nuclear systems were selected by Generation 4 International Forum among the most promising nuclear concepts for our future. In its technological roadmap, the Forum defined 4 goal areas to advance nuclear energy into its next, 4th generation. Sustainability, which requires the conservation of resources and preservation of the ability of future generations to meet their own needs. Another goal is aimed at safety and reliability. Generation 4 system must be designed so that safety margins are adequate, accidents are prevented, and off-normal situations do not deteriorate into severe accidents. Advanced nuclear system should be competitive with alternative energy options from an economic point of view. Proliferation resistance and physical protection are also essential priorities in order to prevent the use of civilian nuclear energy systems for nuclear weapon proliferation. Besides lead-cooled fast reactor and sodium-cooled fast reactor, the other concepts selected by the Generation 4 International Forum are the gas-cooled fast reactor, the molten salt reactor, the supercritical water-cooled reactor, and the very high-temperature reactor. Sodium-cooled fast reactors are not a new concept. The use of liquid sodium was taken into account as coolant in the framework of the liquid metal fast breeder reactors due to the high power density, the low doubling time, and the good compatibility with the structural materials. Sodium fast reactors have been built and operated in US, France, Soviet Union, India, and also Japan. the successful operation of the experimental breeder reactor 2 in the US from 1964 to 1994 paved the way for sodium to become the reference coolant of fast neutron reactors. As for commercial power reactor, good experience came from Phoenix in France and BN 600 in Russia. The SFR system has several good properties. A low melting point ensures a good margin to boiling and the possibility to operate near atmospheric pressure, and hence there is no need for a pressurizer component. A high thermal capacity grants large thermal inertia in case of accidents. Low density allows for a small pumping power, and the good thermal conductivity increase the heat exchange between cladding and coolant. The good compatibility with material and sodium along with the gain experience makes the SFR technology more mature than other fast reactor technologies. The good neutronics features offer the possibility for a best use of limited nuclear fuel resources, considering a closed fuel cycle. In addition, its fast neutron spectrum enables minor actinide recycling. However, there are some issues with the use of sodium that need further investigation. Has the exothermic reactions with water and air, which impact on the reactor design. The use of an intermediate heat exchanger, non-water energy conversion systems, and oxygen and hydrogen control can mitigate this issue. The coolant activation makes shielding more challenging. The low boiling point, along with the possible positive void feedback coefficient, can be problematic from the safety point of view. Provisions in order to avoid and mitigate this aspect should be considered. The opacity of the sodium can be troublesome for the inspection of the in-vessel reactor components and maintenance. SFR is the reference system for fast reactor in Europe. In particular, the efforts are devoted to the development of ASRID, a pool-type sodium-cooled fast reactor with a thermal power of about 1,500 MW. Other projects related to the SFR are ongoing in Russia, US, Japan and South Korea, focusing on both small and large power reactors. Also, lead-cooled fast reactors are not a new concept. In the Western world, during the 50s, fast spectrum systems with molten lead or lead-bismuth alloy were initially considered, but they were discarded due to the corrosion problem of the lead. Notwithstanding, in the Soviet Union, the lead-bismuth eutectic was used as coolant for nuclear reactor for submarine propulsion. In the recent years, there was a renewal of interest for this technology, both for critical and the subcritical reactors. Lead is a coolant with favorable thermal, chemical and neutronics features. The high boiling point of lead reduces the risk of core voiding. The high density contributes to fuel dispersion instead of compaction in case of core melting. The high thermal capacity provides large thermal inertia in case of loss of heat sinks accident. There is no exothermic reaction between lead and water or air, meaning that there is no need for an intermediate heat exchanger. The low neutron moderation allows great spacing between fuel pins. The large space between the pins leads to a lower cross-pressure drops, which also allows natural convection cooling, and it also helps in reducing the risk of flow blockage. Other advantages of lead consist in its good shielding properties and the possibility to employ a closed fuel cycle with an efficient conversion of fertile uranium and minor actinides management. On the other hand, there are also some drawbacks of the lead as coolant. the corrosion due to the use of the lead-based alloy, which calls for coolant chemical control, cladding coating, new materials, and purification technique. The erosion issue limits the lead velocity around 2 meters per second. The high melting point arises the problem of the solidification of the lead. Special provisions are foreseen in order to avoid this issue. The opacity of the lead can be troublesome for the inspection of the in-vessel reactor components and for maintenance. The high density of the lead has an impact on the mechanical design, in particular in case of an earthquake and for refueling. Research is underway to apply seismic isolator to the LFR. Several projects are currently under development, focusing on lead-cooled fast reactor. In particular, Europe is doing research on two main systems. MIRA, an accelerator-driven system cooled by lead-bismuth euthetic devoted to isotope production, material testing, and fundamental research. Alfred, a reactor with a thermal power of 300 MW, cooled by pure lead, intended for electrical power generation. Other projects related to the LFR are ongoing in Russia, Sweden, China, South Korea, and US. Sodium and lead-cooled reactors are a very promising concept for the next generation of nuclear reactor. Thanks to the sodium and lead physical, thermal, chemical and neutronics favorable features, these liquid metal fast breeder reactors can ensure strong improvement in sustainability, safety and reliability, economics, proliferation resistance, and physical protection. SFR and LFR have a great potential. However, they introduce additional research and development challenges in safety, design, and materials that can be faced also thanks to scientific joint activities and education and training programs.
Hello, my name is Didier De Bruyn. I'm working at the Belgian Nuclear Research Center, and I'm going to present you the concept of accelerator-driven systems, or ADS, as you will see this acronym in many references. An ADS consists of an accelerator sending protons with a high energy on a spallation target, which produces neutrons. The target is situated inside a subcritical core inside a reactor. In a previous video, you have learned about the effective multiplication factor, also called Kf. In a classical reactor, we have a Kf somewhat larger than 1. Safety and control rods are available to keep the fission chain stable. In an ADS, Kf is slightly lower than 1, typically 0.95 to 0.97. This means that if we do not have the accelerator, the fission chain reaction will stop. The accelerator provides protons that hit with a high energy spallation target, which in turn produces the additional neutrons. The core is thus intrinsically stable and does not require any safety or control rod. The main advantage of ADS is inherent safety. A conventional nuclear reactor's fuel possesses self-regulating properties, which make these reactors safe. In addition to these physical properties, in the subcritical reactor, whenever the neutron source is turned off, the fission reaction ceases and only the decay heat remains. Many countries have started the engineering design of an ADS. Belgium is studying the MIRA project with an accelerator of 600 MeV, 4 mA, a reactor of 100 MW thermal, and the spallation target being liquid lead bismuth. Japan is studying a larger ADS for the long term, with an accelerator of 1.5 GeV, 20 mA, a reactor of 800 MW thermal,
the spallation target is also liquid lead bismuth. Italy, Korea and China, to name a few, have similar studies running. But the first ADS operational exists already since 2010 at the SEK in Mol with the Guinevere installation. Guinevere has been built in partnership between SEK, the French CEA and CNRS, with a substantial contribution from the European Commission. ADS is a very good tool for transmutation. The next generation of nuclear reactors, the so-called Generation 4, will be able to recycle their own waste. This is not the case for the present generation of nuclear reactors and even the new reactors being built today. So what should we do with all existing waste, called minor actinides, namely neptunium, americium and curium, which are high-level and heat-emitting? In a high-flux reactor, be it a Generation 4 fast reactor as presented in other videos, or in an ADS, transmutation of heavy, long-lived radionuclides is made possible. Both the volume of waste and the required time for disposal would be reduced. This would make deep disposal more acceptable for the public. It is indeed easier to convince the public to build a facility that should be safe for 1,000 years rather than for 1 million years. Think of the pyramids in Egypt. Those are still existing. We can then envisage the combination of reactors using uranium fuel together with other reactors using a mixture of uranium and plutonium fuel. Plutonium is not a waste product, but rather a resource. And finally, we burn the remaining waste products in a dedicated facility. ADS is also well suited for a research facility which is able to perform testing on materials and fuels for the next generation of nuclear reactors. The present existing facilities cannot answer all engineering questions. To summarize, an ADS has 3 components: accelerator, spallation target, and subcritical core. The main domain of application is research reactors and burners of radioactive waste. Thanks for your attention.
Hello, in this video I will explain you the operating principle of the Molten Salt Reactor and the Thorium fuel cycle. Let's first look at a part of the nuclide charge containing the actinides. Along the vertical axis I've plotted the number of protons in a nucleus, and along the horizontal axis the number of neutrons. Each row shows the isotopes of one particular element. The red box, for example, shows the isotopes of the element thorium. And the black or partly black squares indicate the isotope that can be found in nature. Thorium has only one natural isotope, namely thorium-232. Thorium-232 itself is not fissile and cannot be used as a fuel in a nuclear reactor. However, when it captures a neutron, the product, thorium-233, decays quickly to protactinium-233, which decays with half-life of about 1 month to uranium-233. This uranium isotope is an artificial one, but is also highly fissile, just like uranium-235 that occurs in nature. In the thorium fuel cycle, we first need to convert thorium-232 into uranium-233 to fission this afterwards. Because we need one neutron to sustain a fission chain reaction and another one to convert thorium into uranium, we can have a sustained fission chain reaction only if the reactor is extremely efficient with neutrons. Fortunately, reactors like this exist, namely the molten salt reactor. This reactor consists of a large block of graphite, the grey oval shape in the plot, with channels in it. A fluoride salt, typically thorium fluoride and uranium fluoride dissolved in lithium beryllium fluoride, flows from bottom to top through the core and back through the heat exchanger. In the intermediate loop, indicated in blue, the heat is transferred to the energy conversion system to produce electricity or process heat. A small part of the salt is continuously tapped from the primary circuit to extract the fission products from the salt and to add fresh thorium. The safety philosophy of a molten salt reactor is rather different from that of a solid fuel reactor. In a solid fuel reactor, the operator tries to keep the fuel intact and to cool it at all times, even if the fission chain reaction has stopped, to avoid overheating due to the decay heat of the fission products. In a molten salt reactor, the salt is allowed to freely expand and flow. If the salt heats up too much, the freeze plug in the green pipe will melt and the salt will freely flow in the safe storage tanks beneath the reactor core. These can be cooled with water via natural convection or via another passive cooling mechanism to avoid overheating. On the other hand, we should take care not to cool the salt too much, because we do not want it to solidify. The MSR has a strong power feedback coefficient because of the nuclear Doppler effect and the expansion of the salt upon heating. Due to these mechanisms, the power drops sharply if one or more pumps would fill. The left figure shows the temperature of the salt if 4 out of 5 pumps would fill. The temperature rises only some few tenths of degrees, which directly leads to a sharp decrease of the reactor power, shown in the right figure. Surprisingly, also the opposite, an increase of pump power leads to a decrease of reactor power. This plot shows the reactor power of a critical molten salt reactor when the pumps are turned on. Because the precursors, these are the fission products that release a neutron after beta decay, are expelled from the reactor core, the reactor power decreases sharply. If after some tenths of seconds the remaining precursors return to the reactor core, the reactor power increases again. One of the main benefits of the molten salt reactor is the composition of the nuclear waste it produces. This plot shows the radiotoxicity of spent fuel of a typical light water reactor. The red line is the contribution of the fission products, while the blue line is that of the plutonium and americium in the spent fuel. The horizontal line is the reference level, belonging to the natural uranium in the ore and its decay products. In a molten salt reactor, all actinides keep on recycling in the molten salt until they have been fissioned. And this means the actinides will not be present in the spent fuel from a molten salt reactor, leading to much shorter-lived nuclear waste. The reason for this can easily be seen in this plot. Because we start with thorium-232 as a breed material and uranium-233 as a fissile material, we need 4 neutron capture reactions before we produce neptunium and plutonium and other actinides. And this means these actinides are produced in much smaller quantities than in a light water reactor. The molten salt technology has already been demonstrated in the 60s of last century. The molten salt reactor experiment ran for 4 years in Oak Ridge with great success. However, this demonstration reactor contained not yet thorium in the salt, but operated on uranium and plutonium. In this test reactor, also the salt was not cleaned during operation. Nowadays, several European countries work together on the molten salt fast reactor, which has no graphite in the core. This reactor could also destroy the nuclear waste of current light water reactors. As a conclusion, we can state that the molten salt reactor is a very promising type of nuclear reactor, especially in combination with the thorium fuel cycle. It's inherently safe and produces much less long-lived nuclear waste. And thorium could fuel the world for thousands of years. Isn't that great?
The current and modern nuclear power plants are usually based on large-size reactors. Is it a sort of universal law, or can a small-size nuclear reactor possibly designed and built in a modular way be a viable option, or even a competitor in the energy market? I am Sara Boarin and I will guide your initial steps into the intriguing world of the small modular reactors. First of all, what is a small modular reactor? We can define an SMR as a nuclear reactor of small size. Usually the power is less than 300 megawatt electric, whatever coolant technology has been adopted. It may have a design consisting of modules that are typically manufactured in shops and transported to and assembled on site. The dimensions of the reactor, the containment building and the site are smaller compared to the large reactors. Nowadays, the interest in this type of technology is growing. Let's understand why. First, we must consider that SMRs are not the current standard, represented by large reactors. The historical trend is very clear. At the beginning of the nuclear energy era, small-size reactors were the standard, but by 1980, the power and consequently the size of the reactors has increased. The main reason is the well-known economy of scale law. Usually, in the industrial sector, we experience that increasing the size and capacity of a plant is better, because the costs increase less than the size and capacity, thus saving money and time. That means we are reducing the specific cost when increasing the size. In terms of overall costs, the ratio between the cost of a plant with respect to the cost of a reference size plant goes with the ratio of the power size to the power of alpha, with alpha typically in a range between 0.6 and 0.8. So, if this is the trend, why should a small reactor be of interest? There are both specific reasons and potential reasons. In some cases, the large reactors are simply not suitable. For example, because the electrical grid of a country is not developed enough to sustain a large concentrated power production, which could lead to stability risk, or because there is a limited availability of flowing cooling water. Also, the goal could be to supply energy to remote areas where large site infrastructure can hardly be built, or simply because the utility does not have the financial strength to sustain a huge investment of tens of billions of euro or dollars. But there are also more specific arguments for choosing the small modular reactor option over the large reactor. It can be a design simplification that is implemented, allowing cost reduction and innovative safety features. They are usually based on passive safety systems, and the construction time can be reduced, which reduces the overall cost as well, leading to financial risk limitation. Or smaller size entails that it is possible to build and assemble modules in a shop instead of on-site. And the staggered deployment of the SMRs, that means the construction of multiple modules one after the other, allows for the self-financing of the construction of subsequent modules. We could identify a sort of economy of multiples for the SMR technology, counterbalancing or at least reducing the economy of scale penalization caused by the small size. Starting from the specific cost of a large reactor, if we want to deploy an SMR-based power station with the same capacity, for example 4 SMR modules versus one large, the specific cost of one single SMR module, same type of the large reactor, increases due to the loss of economy of scale. But a set of positive SMR features can reduce that penalization. First, multiple small modular units on the same site can share some infrastructures and services. Second, the typical learning process during construction is accelerated for the SMRs, since several modules are built. This means time and cost reduction. This also happens with the modularization of components, systems and plants, which allows shop construction, series production, together with quality increase. And the staggered deployment allows for scalability of the investment, for example, according to energy demand, and together with a shorter construction time and payback time, leads to reduction of the financial cost and risk. The last SMR feature is not just a small replica of the larger reactors, but different solutions and layouts could be applied, potentially involving a relevant simplification leading to cost reduction. At the end of this set of consideration, the cost penalization between SMR and large reactor could still exist, but it is reduced due to the original economy of scale gap.
As a final comment, what we addressed in this first part of the lecture are the main economic features about the SMR concept. Welcome back. This is the second part of the lesson on the small modular reactors. After the basic economic principle of SMRs, we will address the main technological features. Now, let's have a look at some examples of the SMR technology. We have to acknowledge the huge work performed by the International Atomic Energy Agency in supporting the exchange of information and experience among the member countries interested in this technology. In 2016, the agency identified 40 SMR concepts under development, few of them already under construction in 10 countries. Several other countries have already declared their interest in potential deployment. Here's a quick overview of the 3 SMRs currently under construction. The first project is the Russian KLT-40S. It is a compact PWR type reactor mounted on a barge, so it is transportable at sea. The reactor can be used for electricity generation and heat processing. It is also suitable for energy supply in remote regions. The barge hosts 2 35 MW electric modules with a 28-month fuel cycle and a slightly reduced primary system pressure compared to classical PWRs. The SMR exploits both active and passive safety features. Another SMR under construction is a Chinese reactor based on pebble bed, high-temperature helium-cooled technology. The fuel is made of graphite spheres that are roughly 6 cm in diameter, including multi-layer coated uranium dioxide microspheres. More than 400,000 spheres are needed to create the core of this SMR. The spheres can be withdrawn or inserted during the reactor operation. The SMR plant is based on a 2-module single turbine layout for a total of 210 MW electric size. The fuel cycle is 35 months long and the safety strategy is based on passive systems. And finally, there is the Argentinian project, CAREM, with a size of 27 MW electric. This is a prototype of the reference SMR that will be in the range of 150-300 MW electric. It has a PWR-based technology, but with all the main components, such as steam generators, pumps, pressurizer, integrated inside the reactor pressure vessel. The control rod drive mechanisms are also integrated, based on hydraulic systems instead of electromagnetic devices. 12 small steam generator modules are hosted inside the SMR, adopting a helical coil tube bundle and a once-through superheated steam solution. In this SMR as well, the primary system pressure is slightly reduced and the passive safety approach is implemented. The concept of integral PWR is adopted by several other SMR projects. Some of them are in an advanced phase of development and in some cases also in early licensing processes. In the USA, the NuScale project refers to an innovative solution for a 45 MW electric module with a slim and tall steel containment submerged in a water pool and including a reactor pressure vessel with a single helical coil steam generator surrounding the core barrel. A fuel natural circulation is adopted, so no pumps, while a fully passive system allows the core cooling and heat rejection to the water pool. The modular strategy is such that 6 to 12 SMR modules can be located inside the large pool, creating a medium-sized power station up to 540 MW electric. The South Korean SMART reactor has a similar concept, integrating the main primary components, except for a multi-module solution for the helical coil steam generators, a forced circulation, and a larger size, 100 MW electric. Last but not least, the Chinese ACP100 offers an integrated layout, but with the primary pumps placed at the end of the short pipes directly connected to the integral vessel. It is a multipurpose SMR, designed for electricity production, district heating, steam production, or seawater desalination. The site for the first deployment in China has already been selected. A final summary table shows a comparison among different integral PWR type small modular reactors. Several countries are developing this type of reactors, offering a broad spectrum of size for each module and a different level of integration of the components. Almost all the concepts exploit passive safety features, and some of them adopt natural circulation for the normal operation of the plant. As a conclusion of our tour across the small modular reactors, you can find here some key reference documents to deepen the knowledge about this intriguing and innovative concept. Thank you for your attention and get a good reading.
Hi, my name is Guglielmo Lo Monaco. I'd like to briefly introduce you to two innovative gas-cooled reactors, namely the high-temperature gas-cooled reactors HTR, also known as HTGR, and the gas-cooled fast reactors, also called GFR. Both belong to the Gen 4 proposed system. First, let us start with the high-temperature gas-cooled reactors. HTR technology is quite different from other classical nuclear technologies. First of all, the thermodynamic cycle is a Brayton cycle instead of the more diffused Rankine one. Also, the efficiency of HTR is quite high. This is also because of the high helium output temperature, which is higher than 900 degrees. Advanced HTR can be designed both with or without intermediate heat exchangers. The fuel is based on the use of innovative microsphere-coated particle known as TRISO-CP with particularly positive features. It is possible to classify the various HTR concepts on the basis of different aspects. If we look at the fuel element, there are three different possibilities. First, there is the prismatic block type, based on cylindrical compacts inserted in graphite block. Or there is the pinning block type, that is made by centrally perforated fuel compacts with a graphite sleeve inserted in graphite blocks. Also, there is the pebble bed type, that has tennis ball-sized spheres that pass in a full ceramic core without a predefined path. Looking at the balance of plants, it is possible to have both direct and indirect cycles. As to the size, it is possible to design both small modular and large reactors. Finally, it is possible to have HTR designed for electricity production and/or for heat production. This heat can then be used to produce hydrogen. Comparing HTR to LWR, we can highlight some differences. These are often advantages. First, the HTR efficiency is higher. Also, the coolant is an inert gas, namely helium, instead of water, which means the corrosion issues are strongly reduced. Another point is that the use of helium guarantees a single-phase coolant with no phase change, even during accidents. Another difference is that gas turbine technology is used instead of water turbine technology. Moreover, the combination of higher core thermal inertia and lower power density results in possibilities for removing the decay heat. This can be done through conduction to the soil if the plant is built underground. And this means that the design can be less complicated. A final advantage is that there is a high discharge burn-up that could reach up to 700 MWh per kilogram if a pure plutonium uranium-free fuel is loaded. Nevertheless, the HTR needs some development in material technology and more experience with the helium gas turbine needs to be gained. While the prismatic block and the pinning block HTR type operations are relatively similar to LWR management, the pebble bed HTR type operation is quite different. About 360,000 pebbles are loaded in the core with a continuous fuel cycle scheme. The pebbles are loaded and discharged from the plant without shutting down. About 3,000 pebbles are managed daily by the fuel handling system with a frequency around 2 pebbles per minute, and about 350 of them are discarded. Each pebble passes through the core about 10 times before being finally discarded. As a consequence, the fuel handling system is one of the most maintenance-intensive parts of plant. Different helium configurations in the core have been investigated, but all have a common feature. The coolant flows downwards through the active pebble bed to avoid interference with the pebbles passing through the core itself and to partially counteract the establishment of a natural circulation in the case of air ingress accident. Now let's continue with the gas-cooled fast reactors. You might remember that fast reactors in general are important for the sustainability of nuclear power in terms of efficient use of fuel and waste management. GFR have several advantages, as for instance, the efficiency is higher than 40% and there is limited high-level waste production. Also, it has a small void coefficient, although it remains positive. The coolant is an inert gas, helium like in the HTR. Helium is a single-phase coolant with no phase change, even during accidents. Just as with the HTR, there is still a need for further development and experience. For example, the gas turbines and material technology have not yet fully developed. Moreover, gaseous coolants have little thermal inertia, so a rapid heat-up of the core following loss of forced cooling could happen. The lack of thermal inertia of the core structure and the high power density might also cause problems in the heat removal during accidents. Finally, building such very innovative concepts of JFR plants can involve additional issues that will need to be resolved in the future.
What do you think about nuclear energy? Some think about nuclear weapons and waste, while others think about sustainability and cheap energy. We then ask them, what do you know about nuclear energy? This time, their answers were almost all the same. Did you know that one tiny nuclear fuel pellet can release the same amount of energy as 800 kilograms of coal? Or that many countries currently have no final solution for the nuclear waste they produce? During this free online course, you will learn about this and much more from the best nuclear scientists and professors from all over Europe. They will help you understand nuclear energy from the fundamental reactions taking place on the atomic scale to the operation of entire nuclear power plants. So join us this fall for the first edX course on nuclear energy.